privacy, and we'll be giving some welcome remarks, and the start of the first session will be in few minutes. The recording. So hey, so welcome everybody. So I think it's a little bit about past 10 a.m. here Eastern time. So we'll be starting our workshop. So let me share some welcome slides with everybody. So I hope you can see the slides okay. And is the sound okay?
Yes.
Okay, perfect. So thank you. Thank you again. So welcome to the workshop on hardware and architectural support for security and privacy. This is the HASP 2021. And if you want to see our program or see anything about the workshop, you can always go to the webpage here on the bottom, haspworkshop.org. And again, it is my pleasure to welcome you to the 2021 edition of the workshop. This is actually the 10th iteration of the workshop that we've been running, and it's been co-located with either ISCA or micro conferences since 2012. So different years we sort of alternate between different conferences and try to share the hardware and architectural security ideas with the different conferences, and also get different people a chance to attend. So last year we were with micro, and also this year we were co-located with micro. So we're good. We're happy to be back here. And over the years, the goal of HASP has been to bring together researchers, developers, and practitioners from academia and industry to share new research results, practical insights, experiences, and implementations related to sort of all aspects of hardware and architectural support for security and privacy. So presentations will be ranging from more hardware, physical security to architectural security. So kind of try to cover the spectrum. And this workshop is organized every year by myself. My name is Jakub Scheffer from Yale University, also Larry Shih from University of Hudson, and Professor Ruby Lee from Princeton University. So actually, Larry and Professor Lee started it originally, and I joined the organization a few years later. And the most important people this year are the program committee members. So here you can see all the names of the program committee members. So thank you to them for all the hard work. And this year we had a much compressed review schedule. So especially they did really hard work reviewing all the papers in about a week and a half. So this is really fast reviewing. We also had a few program committee members I asked to join a little bit later because we need some expertise in certain areas. So thank you for those who joined kind of late and provided some reviews. And thanks to the reviews and thanks to the program committee members, we got a really good number of reviews for all the papers. So this year we had 17 paper registrations. Each paper received at least 4 reviews, and some papers 5 or 6. So I think a lot of people got hopefully a lot of really good feedback from all the reviewers, and we're happy that there's so many reviews provided for all the papers. And then the review process was as it is typical in a double-blind review. So all the submissions were anonymized. And then we used the popular EasyChair system to collect all the papers, collect the reviews, and then perform the online paper selection, mostly based on the scores of the papers and the author confidence in the scores. There was no rebuttal phase for HASP. In the end, there will be 6 full papers that will be presented today. We also have 2 short papers that were selected for presentation, as well as there will be 3 work in progress presentations. So work in progress, they're not published in the proceedings, but it's a chance for people to present either sort of ongoing work or work that might have been recently published at a different venue. So we'll have a lot of presentation, and also this year we also have a invited presentation from ARM that will be about the ARM confidential compute architecture. So that's also another presentation, although it was an invited, not a submission. And for the workshop format, so we're trying to hopefully keep it interactive, although it's virtual. So for the again, you can see the program at haspworkshop.org/2021/program.html. And then on the program, you'll see that we've divided the workshop into different session. There's session 1 that will start after this introduction. Then we have the work in progress session. Then we have session 2, and then at the end, session 3. So we sort of have three sort of regular sessions and 1 work in progress session. And then for the full papers and then the short papers, there will be 12-minute live presentations by the authors. So again, I'll be promoting the authors to be panelists so they can share their slides and make a live presentation. And then there will be 3 minutes for some question and answer. For work in progress, we'll have 7-minute presentations plus 3 minutes for question and answer. And then there's the one invited talk, which will be 30 minutes, including question and answer. But in addition to the short time after each talk, there will be a author discussion and break period after each session. So on the schedule, you can see that at the conclusion of each session, there's 15 minutes that we can use to basically continue, if there are more questions or we want to discuss with the among the authors. So I'll keep the authors as the panelists so we can have a short discussion and answer more questions. And then the remaining time will be used as a break period before the next session can start. So with that, again, presenters will be promoted to a panelist so they can share the slides and give a talk. And then everybody else is going to be an attendee, and they can only ask questions using the question answer or chat feature using Zoom. So if you have any questions, please send it in the question and answer box or in the chat. All right. So with that, we'll start our first session in about 7 minutes at 10:15 Eastern time. So so please hold on tight. We'll be starting at 10:15 with the first paper on hardware and architectural security. So anyway, if there are any questions, I think now it's a good time to type them in the question box, and then I will answer them now before we start the workshop. So all right, so let's wait until 10:15 to get started. Okay, all right. So we'll be starting in about 5 minutes with the first session, and let me make sure everybody is a panelist. So Muhtadi, can you hear us? Okay.
Yes, I can hear. Okay, thanks.
Okay, great. And are you going to be sharing slides?
Yes, I will be sharing my slides. Thanks.
Oh, okay, great. Sorry, I just saw the phone icon. Okay, great. Sounds good. So we'll start in about 5 minutes.
Thanks. Sure.
All right. So I think we have all the panelists for the first session lined up. So once the time gets here, we'll get started. And feel free to ask any questions. I will not be checking the HOBA webpage. So if there are any questions, please use the Q&A or the chat box. That'll be easier. All right. So while we wait um, to get started, just make sure people have a chance to come to keep up with the schedule. So we'll have the first session starting soon. Will be on hardware and architecture security. We'll follow that with a work in progress session, which will be at 11:15 Eastern time. We have 3 work in progress papers. Then we'll have session 2 at noon, which will be on trusted execution environments, and that includes 3 papers and the invited presentation from ARM on ARM confidential compute architectures, and it will end with session 3 at 1:30 p.m. Eastern time on quantum computer security. So we're covering everything from hardware to architecture to quantum computers and industry. So hopefully it'll be exciting. It'll be exciting workshop. And yeah, since the time is here, Muhtadi, do you want to try to share your slides?
Yes, sure. Let me try to do that. Does that work okay? Are you guys seeing my slide?
Yeah, it looks perfect. So yeah, I think you can maybe in 1 minute can get started, since so there are already so many people here. Yeah, so in that case, I should probably introduce the first speaker. So we're starting session 1 on hardware and architecture security. And the first paper is Sparse, Spatially Aware Laser Fault Injection Resilient State Machine Encoding. It will be presented by Muhtadi from University of Florida, and Sanjay Tajik and Dominic Forte are the co-authors. So Muhtadi, and then Muhtadi is a PhD student at the University of Florida. He got his master's degree from University of Toledo. His research passions include vulnerability analysis of designs. In his leisure time, he would like to travel, acquire novel culinary skills, and play tennis. So sounds like lots of exciting activities besides research. So with that, Muhtadi, I think you can get started.
Thank you very much. Good morning, everyone. Delighted for the opportunity to be here. As Jakub said, along with me, Dr. Shaheen Tajik and Dr. Dominic Forte are co-authors of this paper. So this presentation centers on FSM vulnerabilities related to laser fault injection, with an overview of CAD flows preventing them. We named the specific flow acronym as SPARSE, namely Spatially Aware Laser Fault Injection Resilient State Machine Encoding. So the outline of the presentation is that we discuss the motivation initially, go through the threat model, and then introduce the novel metric necessary for our process flow. We then discuss our sparse flow and then the results and the corresponding discussion. So how does laser effectuate a fault? By laser glitching. The laser can be hooked up to a microscope and applied precisely in timed pulses to locally create photocurrents and alter node voltages. In short, if photons with sufficient energy strikes MOSFET sensitive regions, charge carriers are generated, creating a photocurrent which can lead to a fault occurring in the design. An example can be the state encodings. With precise control of the laser, an attacker might transition to the sensitive states in the design, which might reveal secrets. Just to show how it can be done, if the current state of the FSM is, say, for example, 101010, then focusing the laser on the last 2 memory elements can overturn the states in them. The current state would then change from this to this. In this way, an attacker may maneuver the FSM control path. The fault injection assessments have received attention mainly on crypto and data path logic. However, the FSM is critically important as it controls the overall functionality of most systems. We start with an example of fault injection vulnerability on AES FSM. The state transition diagram of the FSM is shown on the right. The data path is shown on the left. The FSM is composed of these 5 states. Each of these controls specific modules during the 10 rounds of AES encryption. After 10 rounds, this final round state is reached, and the FSM generates a final signal that is critical to the design. For this FSM, we define final round as one of the sensitive states. Because if an attacker can gain access to this final round by bypassing this do round state, then premature results will be stored, leaking the secret key. Throughout the course of this presentation, we have represented NS as normal state and SS as sensitive state. This unauthorized access could be accomplished by injecting false during transitions in the original FSM, or by using the don't care states inserted during the synthesis process. For example, if an attacker can inject a fault to go to this state don't care 1, its next state transition would be the final round, which is the sensitive state. The Patron, which is acronymed form of the pragmatic approach for encoding laser fault injection resistant FSMs, is one of our previous works. How this works is that it omits all the vulnerable states from its allowed normal states by focusing on having distance between all states and sensitive states. So an example is shown here for laser fault injection of 1, which is represented by X. Green color denotes the normal states, orange color denotes the sensitive states, and red color denotes the states that are classified as vulnerable states. The nodes in the center are each of the sensitive states, and vulnerable states have having distance of less than 2. That means that they're accessible from these sensitive states. So these vulnerable states are removed from the encoding. Another aspect is that the attacker may be able to maneuver between these normal states in this scheme, and this does not pose any threat to the FSM. However, Patron does not have design layout into account. This is why we incorporate the layout information of the design in this novel approach. The contributions of Sparse are, first, a novel metric, spatial vulnerability metric, or SVM, is introduced that incorporates and eliminates all the vulnerable state encoding based on the layout placement of the flops. Secondly, to our knowledge, this is the first paper in the literature to optimize the design at both RTL and layout level for security purposes. Thirdly, as shown in the figure, Sparse is integrated with other CAD tools and run on 5 benchmarks, and the results demonstrate the highest security, as we will soon see. Let's look at the threat model based on the design layout. In this work, we assume that we're dealing with a strong, knowledgeable attacker who has physical access to the subject device and a high precision LFI system. The attacker's goal is to bypass the normal flow of algorithm and transition to the sensitive states from normal states in order to get critical information from the design. Specifically, he can precisely overturn single and multiple bit flips in the flops represented by X of the total flops represented by N. The other variables that are studied are the number of affected flops, the normal states and the sensitive states, the normal flops and the sensitive flops, as we will soon explain these terms, and dependence of concurrent bit flips on specific layer locations. So in this work, we study all these variables and their interrelationships, which were previously unexplored, and determine their characteristics so LFI attack would not be successful. So this slide shows why we need a new metric, namely Spatial Vulnerability Metric, SVM, compared to VM, which we proposed in our previous work, Patron. VM simply indicates the total vulnerable states in the FSM that is excluded from the Patron encoding. So according to Patron, the number of faults equals the number of lasers. In Sparse, however, we say that they're not equal and depends on the layer coordinates. The figure on the left shows a flip-flop layout arrangement in which the attacker can overturn any combination of flops. The encoding that we get with Patron will have VM equals to 0, meaning that there are no vulnerable states. However, with the layout information in the account, some vulnerable states may still exist as seen, with later fault equals to 1. So Patron only removes these vulnerable states. So while a straightforward countermeasure could always be utilizing additional resources, with an efficient placement strategy, a better solution can be achieved. For example, if the sensitive state is all 0, then removing only 0110 according to this placement makes this FSM protected, because as you can be seen, flip-flop 3 and 2 are close together. To that end, we deduce that we need a new metric, and the vulnerability metric is not enough. So we propose the related terms that we introduce in Sparse in these slides: spatial vulnerability metric, sensitive flip-flops, and normal flip-flops. Spatial vulnerability metric, or SVM, is the total spatial vulnerable states in the FSM divided by the total states in the FSM. Naturally, we don't want any vulnerable states depending on the layout of the design, so a value of 0 is desired. And sensitive flops have distance constraints, that is, they must be placed at a certain distance away from each other and all other normal flops in the design, whereas normal flops have no placement constraints. So I'll provide an example here regarding SVM, SFF, and NFF. So in this figure, SFF is represented with red rectangles, and NFF is of light green color. So we assume that the flops are arranged in such a way so that the layer spot can only affect the normal flops at once. This arrangement, with this arrangement, it's easy to see that the vulnerable flop combination would then be all these individual flops will always be there, and of course the flop 1 and 2 combined together because they're in close proximity. So if we remove these spatial vulnerable states encoding from according to this layout, then the sensitive states would be saved from the attacker, which is this SVS set according to the vulnerable flop. So an interesting aspect that we will see in the result section is that whenever we see an SVM is greater than VM case, it means that at least one multiple fault is there according to the placement of the flops. In this slide, I will talk a bit about each of the components of Sparse. The goals of Sparse are to find a flexible encoding that is optimal to total number of flops and the number of sensitive flops for which SVM is equals to 0, according to the FSM design specifications, and also subsequently generate placement information of the flop in the FSM. And Sparse can also explore different SFF to NFF ratio, which is indicated by R. The first component is the first 2 boxes here. According to the FSM characteristics and L5 capability, we initially have an iteration. As Sparse iterates, the sensitive state encoding may be updated in this block to feedback from this adjacent block, which is the HGGen. This HGGen block is responsible for generating normal state encoding and identifying the sensitive flop set. So binary decision diagram, or BDD, is used to achieve this process. In the event that the design constraints cannot be satisfied, HGGen has 2 paths. So in the first path, it increases the R, which is the SFF by NFF ratio, and then rechecks if the FSM design characteristics has been met or not. If it's not met, then it increases the total flop of the design, and the output is then passed to the next block. So this third and fourth component deals with the floor plan optimization and placement steps with the SFF information and the flip-flop dimensions and SFF interdistances as inputs. Initial linear programming is used, with which we obtain the area optimized SFF and NFF Cartesian coordinates of the design, which is later then inputted in the EDA tools. So in the results section, we demonstrate our scheme with some traditional encoding schemes like binary, one-hot, etc. We also show the normalized AA values here. All the values are normalized with binary except for memory controller benchmark. In our previous work, it was seen that the memory controller benchmark performs better with one-hot encoding. by that I mean that it has better PDP values. Right. That's because with this encoding scheme, the decoding logic is simpler. And just to note, by code tables, we mean that the nearest NKD linear code and A-Nahian approach. This proposes an LFI scheme that may work with LFI, but at the expense of more flops. So in some of these approaches, we see how the VM is equals to 0 as seen, but SVM is not 0, and SVM has some values, signifying that at least one pair of sensitive flops are vulnerable in the design due to their placements. So in summary, we see that only sparse is guaranteed to have all VM zeros and SVM equals to zeros. So both these values are only zeros for sparse. Occasionally, both these values can be zeros for other approaches like code tables, as we see one values, all zeros. So this can be attributed to random luck in the optimization steps, and there's no guarantee like sparse for these other approaches. Hence, we can conclude by saying that sparse outperforms better than the other security unaware methods in terms of both security and overhead. So with that, we reached the end of the presentation. Thank you very much for your patience.
All right, perfect. Thank you so much, Muhtari, for the very nice talk. And again, we have probably a minute for one question, but also again at 11 a.m. Eastern there will be a discussion with authors and a break. So we ask that all the panelists stay until the end of the session, so we can ask and discuss more then. So I didn't know if there are any questions in the chat. Anybody brave enough to speak up, or type their question. If not, please think of your questions until the end of the session where we can ask some more. I did have one question. I was kind of curious, your method, your threat model assumes that the attacker can have multiple lasers. And I was just curious, what is like a reasonable number? So the chip has a fixed area. So physically you can't fit like infinite number of lasers over the chip. So is there like some practical limit to the number of lasers that an attacker can use?
Yes, mathematically there's no limitation, but as of now the practical limitation is, as per my knowledge, it's two, based on some industry manual, 2 at this moment. Whereas okay. The solution that we show here, it can have as many as the attacker wants.
Right. No, that's really good. So it's very scalable. I was just kind of curious, what's the state of the art in terms of the actual attackers. Okay. All right. Great. So thank you so much, Muhtari. So we might have some more questions at the end of the session, but now we'll go to the second talk. So maybe if you can end sharing the slides, and then Hwajin can share. Hwajin can share his slides. So the next talk will be about Intrust IoT, intelligent ecosystem based on golden dataset-free power profiling of trusted devices in IoT for hardware Trojan detection. And Hwajin is the speaker, and he received a Bachelor of Engineering degree in electrical engineering from Salahuddin University in Hebril. Then he attended Tennessee Technological University from 2015 to 2017, where he obtained a Master's of Science degree in electrical and computer engineering. He attended Tennessee Technological University from May 2017 to August 2021, where he obtained his PhD. So congratulations on recent PhD in electrical and computer engineering. His research interest is in field of cybersecurity, machine learning, and deep learning. So with that, yeah, we're looking forward to the talk on the Intrust IoT. Go ahead.
Good morning. Good morning, everybody. Do you hear me good?
Yeah, the sound is good.
Okay. Good morning, everybody. I'm Haujin. I forgot to mention that right now I'm assistant professor of cybersecurity at Penn State here in Altona. So I will introduce. I will present my paper, Interest IoT, intelligent ecosystem based on golden dataset free power profile of trusted device in IoT hardware Trojan, which is this paper is talking about collecting some power profile from the IoT devices after the chip has passed all the tests and end up on the IoT device and shipped to the market. Then from the power profile can for the IoT power profile can we detect this work was done with a couple of people. One of them is Mr. Paya, Mr. Powell, Ms. Gabriella, and Dr. Said Hassan. So the outline for my work, I will start with some introduction, then motivation, then the problem formulation, then I will go to the section of the paper, the Interest IoT device. So Internet of Things can enable seamless connection, interaction, information exchange between them and their surrounding environment. The growth of IoT device that today every device is connected to the internet and the attacker has access, maybe they has access to them. The growth of the IoT and large scale integration of IoT device, new security threat arise while traditional security issue become more severe. Now the hardware Trojan can change the security functionality, can leak secret information, and maybe can disable the circuit entirely. So the major concern is when the adversary is at the foundry, since most IC are fabricated off the shore. So when we send the layout to the fabrication foundry, the attacker maybe has access and change the layout and give us some problem. So, and the hardware Trojan is of two type. The one it's always on that has only the payload, or there's one with the trigger, the payload and the trigger. When the trigger receives some signal that activate the payload, and the payload is responsible for the malicious activity. The motivation is to detect hardware Trojan attack without depending on the untrusted device golden data set, along with no requirement for design time intervention. So before the works was to implement some design intervention in the IC to detect to protect the IC from Trojan, or we are collecting the golden data set, then checking the golden data set, but accessing the golden data set for the IC is not easy. So most problem formulation, most embedded system employ software security tools to protect. They can be defeated easily by hardware attack if special constraints are not given throughout the development and the design process. Traditional detection mechanism like firewall or intrusion detection system, they cannot detect the hardware-based attack because the firewall and intrusion detection system, they are working in the application layer usually, but the hardware is in the hardware level, which they can pass the firewall easily. Many existing hardware intrusion detection technique require the design time intervention in either IC or the PCB design. So in trust, existing solutions are invasive, require expensive design time intervention, or need data set generation from non-trusted resource constrained IoT or RC IoT devices, or maybe both. RC IoT devices require a final line of defense against possible hardware Trojan attack that go undetected during the IC design or IC test, and the chip or the IC end up with the IoT and ship it to the market at the end consumer house or the building. A defense methodology has been proposed, which are trained on the data set obtained without design time intervention and use only the trusted RC IoT devices. data set, which is the power profile for the RC IoT device. So in this work, we have some scenario. We have 5 scenario. 4 of them is we call non-zero day attack, and 1 scenario is the 0-day attack. The 5 scenario, we collect the data for the IoT when the attacker is off, or the attacker is idle, or the attacker can do some attacks on the IoT device. We collect the data from the trusted device. So in time design intervention, we have the trusted IoT device connect to the same real power for the untrusted IoT device. So the trusted device and equivalent model of that is connect to the same, and we collect the power from the trusted device. The power profile has been generated, then using some benchmark for the testing on the IoT device. Then we collect the data set has been collected using some machine learning and explore the design space exploration to select the best algorithm to detect. Then we use the trained algorithm in the real time when we collect the data from the trusted IoT device with the untrusted device connect to the same power rail and loading some benchmark to the IoT device. Then we were able to detect if there's an attack, if the untrusted IoT device is running any attack on the IoT device without collecting the power consumption from the untrusted IoT device directly, or measuring the power profile of the untrusted IoT device directly. So the data data generation, normal power profile and normal power profile are generated using the trusted device, and abnormal power profile are generated using the trusted device that are connected equivalent to the equivalent model to the trust. So the trusted device is connected to the untrusted device on the same rail, and the power profile as shared the power rail. We run some benchmark application on the IoT device, then we collect the normal power profile extracted from the trusted IoT device with some abnormal power profile extracted from the trusted IoT device that's connected to the untrusted IoT device. And this is the data that we use for the training and validation of the machine learning. So design space exploration, set up, let me move this one, okay. Design space exploration steps involved to train the different machine learning algorithm to generate power profile. So the trusted power set went through the pre-processing, which is combining the label and the clean data set, then selecting select some machine learning and train the machine learning, then use some of the data to validate if the machine learning has the accuracy, then perform analysis based on the hardware accuracy and choose the best algorithm or the best machine learning that detect with the higher accuracy that detect the hardware Trojan. So the trust ecosystem for the hardware Trojan detection during the runtime, the step involved for the hardware Trojan detection using machine learning, proposed machine learning. So we load different benchmark to the or real time to the trusted IoT device that's connect to the untrusted IoT device on the same power rail. We collect the power profile from the trusted device only, while untrusted device, they are working in their maybe in normal case or off case or maybe attacker case. So we collect the power profile from the trusted IoT device only, and we collect the power, the voltage, the current, and the shunt voltage. Then we use this in real time with the machine learning. We route in real time to detect if one of these untrusted IoT device is in the untrusted case, or they are doing some attack. So the result in non-zero-day attack When we collect the data, we found all the power. Why we collect the power, the current, the shunt, and the voltage, all of them, because we found all of them is contribute to the final accuracy of the attack. And when we combine all the data cases, we found that we can increase when we use all the metrics for off idle power depletion denial of service. We found the 50% of the 57% we can detect the type of attack. But when we combine the cases, because we have 4 cases per each scenario, we were able to increase the accuracy to 75%. And don't mention that when we use only 2 the scenarios, when the IoT, when the attacker is off or when the attacker is idle, the accuracy was 99%. For non-zero day attack, we train the machine learning only on the train it on the trusted IoT device without using the power profile from the untrusted. Then we use the untrusted power profile that collect from trusted IoT device in the runtime to detect the attack. And we use for the cover channel attack, we found that the accuracy is reduced from 99.4 to 24% when the attacker is sending a string or a file of 1 kilo or a file of 10 kilo. We found that the accuracy reduced, which is what we are looking for, reduction in the accuracy because of the attack in the system. Then the conclusion, the non-invasive approach is proposed that can detect hardware Trojan through the power profile of RC IoT device, a complete trust ecosystem for the detecting hardware Trojan in the RC IoT device is proposed without design time intervention and with data collection only, the data collected only on the trusted IoT device without including the power from the untrusted IoT device. And for future work, maybe we study the scalability, how many untrusted IoT device we can put in the real power, and we can detect the case or the state of the untrusted IoT device. And we'll try to study the effect of aging when the device is old, how that will affect the power profile of the IoT device. And thank you.
All right, perfect. Thanks for a great talk. And again, we probably have time for one question, but at the end of the session, we have the author discussion, so we can ask more questions there. But yeah, if you're still thinking about questions, I have one question about the untrusted device model. So if I understand it correctly, you train your algorithms on this untrusted device model because you don't have the access to the physical untrusted devices. And do you ever somehow validate that the untrusted model, corresponds to the real untrusted device? Like how is the model developed?
So if I understand your question correctly, so what we collect here is the power profile of the trusted device. So the trusted device is connected to the same power rail of the untrusted device. So we didn't collect anything from untrusted device. So the untrusted device is working without being touched. Only the power profile we collect was from the trusted device. But because of the attack or the process on the untrusted device, the power profile on the trusted device was affected. Using that power profile on untrusted device, on the trusted device, we were able to detect if the untrusted device is in the normal state or maybe in the attack state.
I see. And I guess, can you clarify what the untrusted device model was used for? On one of the slides, you had like a UTM or TUM, like an untrusted device model.
That was the untrusted device model that we trained. Then we used in the real time a normal device that connect to the power rail to detect if the model it's aligned with the real IoT device.
I see. I see. Okay, perfect. Thanks so much. So great. So again, we'll have some time for discussion at the end of the session, but now I think it's time to switch to the last presentation in the first session. So maybe thank you again. And so Tianwei can present the last paper. So the last paper in the first session is practical and scalable security verification of secure architectures. And Tianwei Zhang is a assistant professor of School of Computer Science and Engineering at Nanyang Technological University. He received a PhD in the Department of Electrical Engineering at Princeton University and bachelor's degree at Peking University. Tianwei has a broad interest in system security. For more details, you can see his research projects and publications on his webpage. So great, Tianwei, so take it away.
Thank you for the introduction, Jakub. Good morning, everyone. This is Tianwei Zhang from Nanyang Technological University of Singapore. And we are very happy to present our talk titled Practical and Scalable Secure Verification of Secure Architectures. This is a joint work with Professor Jakub Seifer from Yale University and Professor Rubini from Princeton University. Okay. So over the past decades, we have seen different types of security-aware architectures. So these security architectures try to enhance the process hardware to protect the applications, the data, and the code. For instance, some secure architectures try to isolate the trusted software modules from untrusted operating systems. And in a virtualized cloud servers, the secure hardware try to protect virtual machines from the untrusted but high privilege hypervisors. So we have there are different types of secure processors being designed and also even commercialized. They are known as a trusted execution environment. For instance, in the academia, we have the Bastion, Hyperwall, DataSafe, CloudMonet, Sectum, and MI6. And in the industry, we have seen the Intel SGX, AMD SEV, and in ARM Trust Zone, which have been released and being widely used for different types of scenarios and applications. Okay. However, when we try to design these security-aware architectures, one question is we need to check if there are any potential vulnerabilities in the design. These vulnerabilities are very severe because it can totally disable the secure mechanisms, and we must be able to figure out these vulnerabilities before we fabricate the chip. Okay. So for instance, some researchers and developers try to run extensive tests or simulations to find these design flaws, and others try to perform the informal security evaluations analysis. However, there is still a lack of the systematic method to verify if the secure architectures are really secure or not. This is a challenging task because the secure architectures can be very complex. So for instance, architecture can have multiple different types of the principles, like the end users, like cloud servers and the trusted parties. And also even inside one server, there can be multiple layers of the software components, middleware components, and hardware components. And these entities and the components have high extensive interactions with each other. So it is really difficult to consider, to model all these interactions and discover the potential security vulnerabilities inside the design. So contribution of this project is to propose a new security verification approach, which has two benefits. The first one is the approach, we design approach to be a scalable one, which is able to verify the very complex secure architectures. We achieve this by break the verification task into the external verification and also internal verification. Okay. External verification, it refers to the external protocols between different servers and users. And the internal verification refers to the interactions of different components inside a server. The second benefit of our approach is it is very general purpose and it can be applied to different architectures. Users can even choose different tools they prefer to implement the verifications based on our approach. To demonstrate our approach is practical, we present two case studies. The first one is to verify a secure cloud server hyperwall with model checker tool, Murphy. The second case study is to verify a distributed secure system cloud.net with a network protocol verifier, ProVerif. Okay. So this is also the outline of my talk. We will first present the methodology and then we give two case studies. Okay. So the key insight of our approach is to break the verification into the external verification and internal verification. Okay. So for external protocols, this talks about the interactions of systems with distributed or remote entities. For instance, there can be multiple different types of the servers and the remote users, customers, and also like the network components. Okay. For the internal interaction, it talks about the internal interactions within the cloud server or local systems. There can be interactions between different hardware components, processors, and from the software layer, we have the interactions with the hypervisor and operating system, and also different types of application modules. And even there can be interactions between the hardware modules with the software modules. So this is what we will focus on for the internal interactions. So basically, we will focus on these two types of the interactions individually. And also we break the execution of the architectures into different phases, as shown in the figure in the slide. Okay. We have the system start up, and then at the runtime, we have different stages. This includes the protection initialization, data code runtime, configuration update, and data code migration, and also protection attestation. And then there can be code data termination. And finally, we have system power down. So we will also focus on the verification of different execution phases individually to achieve the scalability of the verification. Next, I will give a brief introduction about the steps we need to perform verification. There will be 3 steps. The first step is to model the systems. Okay. We need to specify the essential components to describe the systems. For the external protocols, we will model each server, network component, and users. For the internal interactions, we will model the different hardware components and also software components. And more importantly, we need to model and describe the attackers, like these untrusted components and their capabilities based on the threat model. Okay. After we specify these components, we need to build a semantic modeling. Okay. Each component will be modeled as a subject with a set of states, like operations. And the state transitions will be defined by the architecture design. Okay. We have initiator subject with a start state, and we also have a finisher subject with a commit state. And then the symbolic modeling is able to explore all the possible paths from the initiator's start state to the finisher's commit state. The second step is to define the preconditions and the security invariants. Okay. The preconditions is constraints that the protocols and interactions need to follow. And it defines the components that need to be trusted, that need to be placed in the trusted computing base. Okay. And for the security environments, these are the goals that the architecture should satisfy. And this is also we need to check whether they will be violated or can be satisfied always. Okay. So for we consider confidentiality validation, which is to check if the confidential data will be linked to the untrusted principals. We can check if the untrusted principals will have access to this data, or if the confidential data are encrypted, but the untrusted principals have access to the encrypted keys. For the integrity, we will check if the critical data will be compromised by the untrusted principals. And we can compare this data with some known good values provided by the trust party. And we should also check the self-consistency of these values during the operation. Okay. The last step is to implement the verification, the modeling, and also do and also analyze the verification results. Okay. So for implementation, we can choose arbitrary tools for the model checkers or network protocol verifiers. Okay. This will give the designers more flexibility to choose the tools they prefer. Okay. And after that, we can perform a security analysis. If the tools tells us that the protocol or the interaction passes, and we can try to remove some predictions to test their necessity. This enables us to identify the minimum preconditions, the minimum TCB that to ensure the success of verification. If the verification fails, we need to redesign architecture and rerun the verification. We do it iteratively until the verification passes, and we can obtain a secure design without any security flaws. Okay. So here we give two case studies. The first case study is to verify the hyperwall, which is a cloud server to protect virtual machines from the untrusted hypervisors. This is a predecessor to the AMD's SEV extensions, and it introduced new hardware extensions to manage the memory activities and to protect the confidentiality and integrity of the virtual machines. Okay. So we consider the virtual machine startup validation. Okay. So the goal is to check if the integrity of the virtual machine image and configurations are compromised. Okay. So we build the symbolic models between the customers, the network hypervisors, and the processors. Okay. And we specify preconditions, which mentions that the processor and the customer must be trusted. That is, the processor must be trusted with a valid certificate and encrypted keys. Similarly, this is also holds for the customers. And we specify security invariants, which is that the customer is able to reach the commit state with the correct values, not compromised by the untrusted hypervisors or untrusted networks. Okay. Based on this modeling and these conditions, we implement it in the Murphy, and the tool tells us the verification passed. The second case study is to verify CloudMonet, which is a distributed cloud systems to monitor and attest the security of the virtual machines in the cloud. And it involves 4 entities: the customer, the cloud controller, the attestation server, and the cloud servers that interact with each other frequently. So we want to verify if the evidence collection process in the cloud server is secure and cannot be compromised. This is a attestation phase. And we build a symbolic model for a single cloud server. This includes interactions with the OS, the hypervisor, which is untrusted, and also 2 hardware modules, monitor module and the trust module. And we specified preconditions, which the trust and monitor modules are trusted, so as their communications channels. Okay. And the security events we want to consider is that the cloud server can ensure that the measurement, the evidence collection data is correct, cannot be compromised by the untrusted hypervisors. And we implement this modeling and also the conditions using ProVerif, and the results is verification passed. At the same time, it also tells us these preconditions are the minimum requirement. These are the minimal trust TCB that we need to enforce in order to have a correct and a secure attestation process. To conclude, we designed a new secure verification method to verify different types of security architectures and systems. And we also present different case studies, including the HyperWall and CloudMonet. More examples can be found in our paper. Okay. So thank you. I'd be very happy to take any questions.
All right, perfect. Thank you, Tianwei, for a great presentation. So this was the last presentation in the first session. And actually, if you have any questions for Tianwei or any of the first speakers, we'll have a bit of a author discussion / break until 11:15 a.m. Eastern time. So for next 15 minutes, we can discuss anything, or we'll just have a break if there are really no questions. I see there are more and more attendees, but we're not getting more and more questions. So please, you can use the chat window or the Q&A feature. But maybe Tianwei can stop sharing his slides, and then if there are any questions. Oh, actually, there's one question for Tianwei in the chat. So to Tianwei, how easy it is to port the verification to other trusted execution environments, such as Intel SGX or TrustZone?
Thank you for the question. This is a good one. So basically, it depends how we model this commercialized TEEs like the SGX and the trust zone, because the complexity depends on the granularity of the modeling. So basically, so like if we try to verify another TE like the AMD SEUA, so this will be similar as Hyperwall, which we presented as a case study. And for Intel SGX and the trust zone, this will be also like some execution phase for verification of some execution phase will be also similar. So for instance, like the Intel SGX and the trust zone, they also have provided the attestation services enabling the remote users to query to monitor the security of the enclaves and also the applications running on this trust zone. So this will be quite similar as the verifications of the attestation we just showed in the Carmel net. So I believe there should be some similarities between the verification of the this TE with our case studies.
Okay, perfect. Yeah, so yeah, how to make it more scalable. That's really good target. Great. I had some questions for the first two authors. If there are no more questions in chat, but feel free to type away. I guess I had a question for Muhtadi for the first talk again. It was really cool about this laser fold injection. I was curious if when you use the laser fold injection, whether the faults are correlated, if one laser can affect multiple flip-flops, and is that something that's accounted for in the model, or even if the same laser hits, let's say, two flip-flops, you assume that the faults are sort of somehow independent?
Thank you for the amazing question, Jakub. Yes, as stated in one of the slides, as we mentioned, that we had a work previously, which was Patron, and it assumed that we have when there's like laser fault injection equals to 1, which means that the laser is actually focusing on one of the flip-flops or two of the flip-flops, and at that time, considering that work alone, we assume that X is equals to 1, which means that only one flop is being attacked. Whereas for this sparse method, we see how we have differentiated Patron with sparse in terms of a new parameter, which is F, which means that the number of faults that each X can effectuate faults upon. So that means that one laser can actually effectuate multiple faults. So in that sense, yes, sparse can incorporate multiple faults into the design, and it's also there in the mathematical model.
Right. I was kind of curious for when you have multiple faults, are you assuming they're correlated, or even if there are multiple faults per laser, each fault itself is sort of random and independent?
Oh, okay. Sorry, I did not get that part. Yeah. So we are actually assuming that it's independent.
Okay, perfect. I didn't know how it works. Okay, great. And actually, there's a question from the audience, a sort of follow-up. Have there been recorded instances of laser fault injections attacks in the wild? So yeah, do you know of any examples of these attacks actually happening? Or it's I guess it's hard to know unless somebody advertises that we're attacked.
Yeah, as far as I'm concerned, I think I read a couple of papers. Like in one paper, I remember that it was published in Host. It was in the AS last round. The author was able to successfully attack the last two beats of the round, and I'm not really 100%. I cannot recollect all the information out there, but I will talk to the person who questioned it. So I'm going to do some research and get back to him about this, if that's okay.
Okay, yeah, that's perfect. Yeah, so Sylvia Losa was asking the question, so that's great. Cool. I had I don't know, just to maybe stimulate some discussion. I was actually wondering whether how this might work with the hardware Trojans. So for Hwajin was talking about trying to detect the hardware Trojans, but I don't know, do either of you have some idea? So for example, could the laser be used to somehow try to trigger the Trojan to see if there's a Trojan there, or do you, I don't know, is it even possible to kind of use this laser as a defense in some sense to kind of, see if there's some dormant logic, and maybe you can trigger some logic that you were not expecting to be there, and you could find the hardware Trojan? I don't know if that's even realistic.
I think currently we have an ongoing project where we try to incorporate all these concepts to combinational part of the logic, and we are working on it right now. So right now, Patron and Sparse, they only deal with the flip-flop part of the design, and we are trying to expand on it. And I think after that, there's definitely some way in which we can incorporate the Trojan part there. Okay. For sure, that's my understanding.
Okay, that would be really cool. I think it can, even with the registers. I mean, I guess some of the Trojans, they have some registers to compare the trigger value, so it might be interesting. But I guess yeah, that sounds really good. I don't want to keep talking about just the first paper, but that's really good. And for the I don't know, for the power profiling that Hwajin was talking about. Hwajin, I don't know if there's some interesting future work or next steps that you're looking at that might be interesting follow up in terms of defending these IoT systems from untrusted manufacturers.
So for the hardware Trojan that you asked the previous presenter, the Trojan, the definition of Trojan, that we have the payload and the trigger. So the trigger can be activated in any way. So if it's using an outside, maybe a laser, a microwave, or anything, that so can be a part of the activation to the Trojan. For the future work, yes, one of the future work that we are trying to do is trying to study the scalability, because today, for this time, our work is to detect a malicious operation on IoT devices without measuring the power profile or the power directly from the device. And what we used here, for example, we used available IoT device that compare the computation and the memory is, or the power consumption is compatible with the most IoT devices on the market, like Raspberry Pi 0, Raspberry Pi 3, Raspberry Pi 4. And we use these devices as the model. And actually, we use the same devices for the real-time detection. But in the future, we will try to measure the different model, measure the power profile for the different model and compare with different IoT devices that are available on the market. So, but for today, or in this paper, the devices that we use as a model and in real time was almost the same, or they are the same. But one of the future work, as I mentioned, it will be measuring the power profile of some devices and comparing to the same capability of other device. Can we detect or not the device, and the effect of the aging? For example, if one question was, is this attacker is available, if someone who did it on the laser in the wild, so if we put some IoT device in the wild and after 1 year, 2 year, is the power consumption of that device will affect the processing or the consumption of the device, that will lead to actual detection, or maybe to false positive on the machine learning algorithm.
Okay, great. That I think that yeah, the kind of once things are in the wild, that becomes quite interesting with all these attacks. So maybe just one last question before we take a short break before the next session. So for Tianwei, one of the earlier questions talked about SGX and trust zone, and in the verification that the work has focused mostly on academic architectures where you know the details of the architecture. So how difficult do you think it's to model the architecture if it's something like SGX, where you have the manuals but you don't have the actual source code of the design?
Thank you for the question. So definitely, if we have more information, it will be easier for us to do the modeling and to do the verification, because this approach is originally designed. Proposed for the designers to verify their designs. So if you do not have much knowledge about the architecture design, and this is a totally black box for us, so it will be not easy to perform verification. And also, this is not easy for attackers to use our approach to figure out any potential vulnerabilities and then explore the vulnerabilities to attack the secure architecture designs. I think this will be the trade-off. Anyway, to verify the architecture, this really depends. So basically, because the more the finer granularity we have to model the architectures, the more accurate results we can get. So if we have detailed information, we can model the architectures in a very detailed way. But if we have limited knowledge, we may model the architectures in a more abstract way. This can give us sort of insights about the security of these architectures. Yeah. Hope this answers your question.
Yeah, that's really cool. So okay, great. So I think we're out of time for for the discussion. Maybe we'll take a 1 minute break until 11:15 a.m. Eastern time, at which point we'll start the work in progress session. And I think so we'll have a break now, and I think all the panelists should be set up for the next session, and I'll remove the current speakers from the panelists. So so we'll start with the work in progress session in 1 minute. Yeah, so by the way, if you are a panelist or if you're a speaker in the work in progress session, please accept the promotion to panelist. I can invite you to be a panelist, but I cannot force you to to become a panelist. So okay, all right, perfect. So great. So with this, I think it's 11:15. So we should get started on our second session, which is the work in progress session, and we'll have three work in progress talks. So maybe Sylvia can share her slides. I'll give a short introduction. So the first work in progress presentation is Vulnerability Tree, a taxonomy of hardware and software computer attacks for heuristic hacking defense. And the presenter is Sylvia Losa, who received a bachelor's in psychology at Florida International University, a master's in mental health counseling in Nova Southeastern University, and then practiced as a therapist for several years. Following that, she worked at a cognitive neuroscience lab at the University of Miami. Changing careers in 2019, she received a bachelor's in biomedical computer engineering from Florida International University and is currently pursuing a doctorate in computer engineering from the University of Colorado at Boulder. So this is really cool having somebody from so many perspectives to talk today. So so Sylvia, please take it away.
Thank you, Jakob. So today I am presenting the vulnerability, which I developed with Anji Shume and Tamara Lehman at University of Colorado Boulder. So our motivation is that there are numerous computer-based attacks on both hardware and software. The National Vulnerability Database has 18,362 from 2020 alone. These are novel attacks based on other attacks, and there is no comprehensive taxonomy of vulnerabilities that combines both software and hardware. There are existing databases of attacks that have some taxonomical information, but there's no visual presentation of all of them comprehensively. So our main goal is to provide a visual future-proof tool for understanding the relationships between vulnerabilities. And hopefully that will help researchers and people in the industry predict new types of attacks by seeing the relationships between attacks. So our key contributions, we are doing this all open source. It's a ranked hierarchy of attacks organized by target. Each level of this taxonomy was picked logically. So another contribution is tying hardware and software attacks together in one place. A lot of industry focuses just on software-based attacks, and hardware attacks are just as important. So tying these defenses together also with attacks in the same taxonomy structure is important so that we can see how the defenses are also related. We use modern web crawling tools to keep the database evolving with state-of-the-art information. There were attempts at creating comprehensive taxonomies over time. None of them have stayed current because they haven't. It requires constant updating. There's no human that is working to do that 24/7. So we implemented some web scrapers that just comb these databases like the CVE and as part of the NVD, and just update the database constantly. So our design is that we have a taxonomy with target-based levels, and there's increasing specificity from the domain level all the way down to the individual vulnerability. And we tried to use existing taxonomies. There are some individual taxonomies for certain specific attacks, no comprehensive ones. So we tried to, as much as possible, incorporate the already the smaller taxonomies into our bigger taxonomy. And then we also have an SQL database with 4 hierarchical tables, a multifactorial classification system, and the tree structure is populated automatically, as I said, by the web scrapers. So as you can see, the tree structure is basically already designed. We have the taxonomy built, and the only thing that happens is automatically is the attacks populate. So each level is based on logical distinctions. For example, the domain level is divided into hardware versus software, and that's where attacks get filtered in. And then there is the abstraction level with the component, physical, and input-output under hardware. And then in the organization level, it's physical and software components. So like the processor, the RAM, the cache. Under physical, there's social attacks, there's machine-based attacks. In the operating system, there's buffer overflow. There's more there, but we can't even fit the entire tree structure here in one image easily. So we also include attacks even on like firmware, which would fit based on whether they were attacking the hardware or software, peripherals, etc. And the tree structure, as I said, is pre-built. Attacks and defenses are added automatically. So our methodology is to start with the attack, and then based on keywords, we choose the levels working all the way up to the domain. Oh, and as you can see in this image, we have 2 examples of specifically the Trojan it's a software Trojan, not a hardware Trojan. Those are separate in the hardware attack Trojans. And then this is versus like the flash and flush. And you should be able to, with any attack, simply pick keywords and auto-populate the tree. So the Trojan Croton goes into the Croton group. It's a ransomware type attack, and then it fits into the injection attacks, and internet and software. So future-proofing this, all of it's open source so that we can get input from other people. And also because all of the tools are free. We use web scraping to data mine the attack. And here is sort of an example of what the code, pseudocode of the web scraper. And we auto-populate the SQL database tree straight from the web scraper. So as you can see, we use beautiful soup, we pick a target URL, we import the data, and we create a list to store the attacks. And then we parse the data for those keywords and place it into the table based on that. And for ongoing work, our web scraping tool currently adds attacks to the table, but it needs to use keyword selection to tie in the attack. So right now that's a little tricky, and it works most of the time, but not all of it. So that's why this is a work in progress. And we still need to add defenses. Those are harder because I haven't found many, if any, databases of defenses. So we might have to add those in by hand. And we need to finish the website for visualization of the taxonomy. And then finally, I believe that that's everything. I see that there are questions in the chat. Are there any questions?
Great. Sorry, I was talking to some panelists, but yeah, if there are any questions, please speak up in the chat or use the Q&A feature. And just like for the first session, there will be a short author discussion period at the end of the work in progress session, so we can have more discussions. I don't see any questions from the audience, but I did have one question, whether you considered some other sources in addition to the databases. So, things might be published in research papers before they make their way into the databases, or somebody doesn't submit it. I don't know how feasible it is to scrape, Google for these kind of type of things.
It is definitely an idea we have considered. It's an excellent idea. That would be even further in the future as far as, toward it. That's definitely a goal that we would like to implement eventually, yes.
Okay, great. We have one more minute, and there's one question from Professor Lee. So can you summarize some interesting insights you have found about the vulnerabilities based on your scraping so far?
Yes, what I have found that's really interesting is that a lot of hardware attacks get implemented first, and then you eventually see a similar attack in the software realm later. One of the data points that we keep in this database is when the attack was first seen in the wild, and also when it was first developed. So if it was developed by a researcher or somebody in the industry, that would also be saved. So, and then we are also trying to implement a section with like code examples. So definitely, I think the interesting thing that I found was that a lot of attacks you see in hardware first.
Oh, cool. That's really interesting. That's good for the hardware researchers. Cool. So I think we have to jump into the next work in progress, but we can continue the questions during the discussion period. So thank you, Sylvia, for the presentation. And then USG maybe can share their slides. So the next talk will be mitigate reverse engineering attacks on deep neural networks with lightweight obfuscation. And USG is a fourth-year PhD student at Illinois Tech in Chicago, and Professor Ruja Wang is their advisor. The research study is about computer architecture with primary focus on promoting a secure and efficient memory system architecture. The work in progress paper presented here at HASP is about mitigating reverse engineering attacks that exploit memory access patterns that could leak some information about deep neural networks. So yeah, please take it away. And yeah, thanks for turning on video if you're comfortable. Oh, I think you're muted.
Hi, hello.
Yeah, we can hear you now.
Okay. Sorry about that. Okay. Okay. Hello, everyone. My name is Yue Zhiche. I'm a PhD student at the Illinois Institute of Technology. Today, I will present our work in progress paper, Mitigating Reverse Engineering Attacks on Deep Neural Networks with Lightweight Obfuscation. This work is in collaboration with Louis and Professor Wang. I will start with an executive summary. In recent years, the deep neural networks have become increasingly popular in many applications, such as image recognition and language processing. A well-trained model is considered as an important IP and should be protected. However, the challenge is that many attacks have been proposed to steal the DNN structure. We will introduce a reverse engineering attack through access pattern side channel on DNN. And the other challenge is that the existing protection schemes for access pattern leakages are undesirable for DNN. So we are motivated to propose a new design, LODNN, a lightweight obfuscation framework for protecting the DNN models. Okay, for the background, I will briefly introduce the basic DNN structure. As shown in this figure, DNN contains more than 3 layers, an input layer, hidden layers, and an output layer. During the DNN inference, each layer will pass the results of multiply accumulate of feature maps and filters to the next layer. Eventually, the output layer returns the final result. The reference here is the first paper that proposes the reverse DNN attack through access pattern side channel. In our work, we use the same thread model, where the DNN is developed and running on a hardware accelerator, and the accelerator is connected with a host CPU and an external memory. The DNN accelerator and the host CPU are trusted, while the external memory is untrusted. During the DNN inference, the accelerator will access memory for weights and feature maps. All data is encrypted, but the memory access pattern is exposed. An attacker could obtain the accessed addresses, frequency, and the memory footprint by snooping the address bus. The first step of the attack is to obtain the DNN structure, including getting the number of layers and the dimension of each layer. I will show how access pattern leakage can expose the DNN structure. In this figure, it shows the access pattern of a simple DNN example. The x-axis is the application trace index, and the y-axis is the accessed memory address space. The blue and the red represent the feature map read and write, and the green is the filter read. As we know, the write operations occur when a layer writes the output, which will be read as the input by the following layer. So these read after write operations will may expose the layer boundary. And since the filters are read-only, we can easily distinguish the access pattern for features, feature map and the filter. Also, the dimension of each layer can be inferred directly by the memory footprint. Let's see the existing protection to hide the access pattern of DNN. For example, the oblivious RAM and the shuffle-based obfuscation scheme and the software-based obfuscation scheme. The first, the ORAM reads and writes redundant data and will have significant overhead, especially for the data-intensive DNN application. Also, a typical ORAM does not support multi-thread access and violates the data locality, which makes it too costly. Second, the shuffle-based approach will only shuffle the address space, but it cannot hide the read after write dependency, so it will still leak the model structure. Third, some protection schemes obfuscate the layer sequence and the dimension through the software function. However, those software protections should ensure the new obfuscated model has no effect on the original model's accuracy. So the new obfuscated model can still serve as a new target for attackers. In our work, our insight is that not all access patterns needs to be protected. So we summarize the two critical leakage hints in our work currently. One is read after write dependency, and the other one is the memory footprint. If we could hide those two leakage hints, the attacker will get nothing necessary from the access pattern. We propose LODNN, which focuses on hiding critical leakage hints only. This figure shows a typical DNN accelerator and the overview of our design. LODNN has two parts, a layer divider and a layer shrinker, to hide the critical hints 1, 2 respectively. The first method is the layer divider. I will talk about the general idea of this method, which is to divide one single layer into multiple sublayers. For example, here the figure shows an original convolutional layer. The input data matrix do calculation with the filters and write the output to the memory. In this example, we divide one layer into two sublayers. The sublayer 2 will read the output of the sublayer 1. So if the attacker observes the read after write dependency, he will get one additional layer boundaries. If we could divide more sublayers, then the read after write dependency can be obfuscated. So we can set a divide rate to control how many sublayers are divided per layer. The method detail will be finished in our future work. The other method is layer shrinker. We add a LS buffer to store output feature map on chip, a read-write selector to manage the data flow, and implement an address randomization method to obfuscate the memory footprint. By buffering a portion of output, we can hide the real exposed layer dimension. Our evaluation methodology takes 3 steps. First, we run DNN applications by using Keras, an open source Python library. We could get the model information about the structure and the parameters. Second, we implement the DNN applications in C++ program, in which we can customize the model structure. And most importantly, we collect the access pattern trees. Lastly, the step 3, we use the generated access pattern trees as our input and test the memory cycle in the USIM simulator to test the LODN's performance. This figure shows the result of our ongoing work. We use the VGG16 as baseline. The x-axis is the LODN with different layer divided rate. The y-axis is the performance compared to the original VGG16. As we can see, by adding the LS buffer, our design performance can be better than the baseline. Okay, in conclusion, we introduced the challenging of protecting reverse engineering attacks on DNNs, and our key insight is to hide the critical leakage hints only. In future work, we will enhance our design and discuss the trade-off between the layer divided rate and performance and the security. Also, we will show more DNN applications in the evaluation. Okay, thank you very much.
Okay, perfect. Thank you so much for the nice work in progress talk. And actually, there is one. We have again about a minute. There's one question from the audience. Is it possible to have a theoretical proof that the obfuscation can mitigate all the leakage to the adversary? Can there be an adaptive attacker against this approach?
Yes, we are still collecting more critical leakage hints, but currently we just show the 2 hints from the previous work. I think there will be more.
There'll be possible more attacks. Okay, great. Yeah. And we have more time for questions at the end of this session. So I guess we should jump to the last work in progress presentation in this session. So maybe you can stop sharing the screen and
okay.
Zach can share his slides. So the next work in progress is automatic transient execution attack detection. And the speaker, Zach, is an undergraduate computer science student at the University of Colorado Boulder, interested in all things computer systems. Currently, his research focuses mainly on microarchitecture and spectra attacks, but his projects also combine formal methods with probabilistic programming to give a well-rounded research experience. After completing my undergraduate degree, he would like to pursue graduate school research in the fields of operating systems and networking. So if you're looking for a motivated graduate student, you should talk to Zach. So with that, Zach, take it away. And if you're comfortable, you can turn on the video so people can see you. All right, thanks.
Awesome. Yeah, thank you. Hello, everyone. My name is Zach McKevitt. I'm an undergraduate computer science student at the University of Colorado Boulder. I'm working with Professors Tamara Lehman and Ashutosh Trivedi to present to you my work in progress work on automatic transient execution attack detection. So the type of attacks that we are mainly focused on are Spectre attacks. And for those who don't know, these are processor level attacks that rely on speculative execution to sort of execute code before maybe their permissions get executed. So on this little code block down here, maybe we would speculatively execute line 3 before we necessarily check the array size bounds, and then we could actually learn this attack here. So this is a security vulnerability, and it's actually still ongoing, even though we actually discovered this vulnerability about 3 years ago. We continue to find Spectre variants today. So the key contributions to our work are we actually want to create a platform for software developers to actually determine whether or not their code has Spectre vulnerabilities. So essentially, we want to shine a little flashlight on our Spectre ghost and make him less scary. But we also want to be able to learn Spectre variants that we have never seen before. And we do this by sort of analyzing microarchitectural state and instruction sequences, software side, in combination. The motivation for this work is that prior work seems to kind of look at one area or the other. Either they dive deep into the microarchitecture or they dive deep into the software patterns. And they're also very experimental based. So our work differs in that we actually like to combine both, and we are going to use probabilistic programming, which is a novel programming paradigm based on Bayesian inference to sort of learn new Spectre vulnerabilities. At the end, our goal is, does a given code sample potentially leak any information due to Spectre-based attacks, and can we determine new attacks? To kind of, our methodology for this project is we use the Gem 5 processor simulator to simulate various code segments and produce microarchitectural output traces. We analyze Spectre safe programs that are guaranteed to not have any sort of Spectre-based attacks. And we also analyze programs that we force Spectre attacks into. So we can kind of generate two sorts of traces, vulnerable and safe traces, and we can use these to learn our data set. And like I said, we do this using probabilistic programming, which kind of puts all of this learning under the hood, so we don't have to worry about it. So I mentioned traces from the Gem 5 output. Here is a trace from a Spectre vulnerable program, and it looks a little scary at first, so don't worry, I'll break it down. On the right, we can see that we have a sequence of assembly instructions for a given program. And on the left, there are a bunch of these colors. And these colors actually respond to different stages in the processor pipeline per instruction. So each instruction has multiple colors. So for example, this F is a fetch stage in the pipeline. Then we have a decode, a rename, dispatch, issue, complete, and retire. One thing I want to direct your attention to is the sequence of instructions that have these dashes or these equal signs. And these are actually instructions that get flushed by the processor pipeline. So like I said, this is actually indicative of a Spectre attack. It could be, or it could be something that is unrelated, such as a page fault. These are just instructions that have been executed speculatively that the processor decides we no longer need. I also want to direct your attention to the first flush instruction, this load effective address here. This is important because we use this to determine whether or not these flushings occur due to a branch misprediction or something normal like a page fault. But we'll analyze that later. We'll come back to it. The next thing I want to direct your attention to is this move instruction right here. So this actually moves information from memory into a register. And the interesting thing about this move instruction is that it is flushed, meaning we don't really need it. It's not important. But however, it completes, meaning that we might be able to kind of access this data in microarchitectural caches, for example, even though we're kind of not supposed to be seeing this because it's been flushed. The last thing I want to direct your attention to is this first instruction after the flush, this no op here. This actually allows us to determine whether or not these instructions were flushed to a branch misprediction. As we can see, the program counters between this no op and this load effective address are clearly different. And so this indicates that we went on one branch and decided we don't want to go down that branch and we need to go down another one. So in combination with this branch misprediction and this memory address load completing, we can kind of look at this sequence and we can determine, hey, yes, there might be a Spectre vulnerability in this program. So we use these traces to learn an automaton. So for example, this is an automaton that reflects the Spectre variant 1, which I showed in the previous trace. And we sort of break it down in the same way that I just broke it down for you. So we sort of load our instructions here from the left from our start. And while we see instructions that retire, instructions that don't have those dashes, we'll kind of stay in our state Q0. Nothing is fishy here, we're fine. But as soon as we start to see a flushed instruction, this sort of flags something to us that something might be a little fishy, right? So we'll actually save the program counter, and do keep in mind, this is not just a normal deterministic finite automaton. We do need a single register store to save this program counter. But as we continue to see flushed non-memory instructions, we'll kind of stay in the state Q1. And if we never actually see a memory instruction by the time that we retire, we'll go back to Q0. But if we do happen to see a memory instruction, and remember, that is this move RM instruction here, then we will actually jump to the next, we will jump to the next state Q2. And if it completes, that is another flag that something might be up. We'll move to the state Q3, and we'll stay here until we examine that first retired instruction. In the last case, that was our no operation. When we come across this retired instruction, if we see that their program counters are the same, this case here, this is indicative of something like a memory fault, which we believe is not vulnerable. We do not believe this is something to worry about. So we would jump back to our state Q0. However, if we see a difference in program counters, like we did in the trace, the difference between the load effective address and the no operation, we'll actually jump into this Q accept state. Now, the important thing to keep in mind about this automaton is if we ever jump into this Q accept state, this will flag a Spectre vulnerability. However, if at any point we kind of end our instruction stream, we've reached the end and we're in either state Q0, 1, 2, or 3, this is indicative that a Spectre attack is most likely not occurring. So we would actually like to use our probabilistic programming, the novel paradigm that incorporates Bayesian inference, to actually learn automaton like these for Spectre variants that A, already exist, but B, also new ones that we've never discovered before. And we would also hope that these automaton are easy for developers to sort of insert their code on the left, and then it will spit out, hey, you have a Spectre vulnerability in your code. You might want to check that out. Or, hey, you're all good. No Spectre vulnerabilities here. This is kind of a breakdown of our methodology. So like I said, we generate safe programs. These are programs that have no Spectre vulnerabilities, and vulnerable programs like the one that I showed the trace for earlier. We input these into our Gem5 simulator, which will output us multiple sets of safe traces and a set of vulnerable traces. And we input these as a set of examples and counterexamples for our learning algorithm. Now you notice there's a little input from the user here. This actually requires a user to put in kind of their guess automaton. So for example, our user here, he might say, oh, I know a thing or two about Spectre attacks. I'm not really 100% sure how they work, but here's sort of my guess. And our learning algorithm will actually use our examples and counterexamples to fine tune the automaton and actually output a full single store register automaton like I showed you in the last slide. So the future work, as this is a work in progress, are to actually develop a working model for automaton learning in Pyro, which is a probabilistic programming language based on Python. We also need to generate multiple sample traces of the different Spectre variants. Currently, we are just examining Spectre variant 1, although many variants do exist that we plan to incorporate into our learning algorithm. We need a way to easily convert Gem5 traces into something readable by the computer. That trace file that I showed you earlier is very human readable, but not very computer readable. And lastly, we want to learn these automatons to actually describe the multiple Spectre variants. Once we do all of these things, I believe we will have a great tool for not only learning new Spectre variants, but also helping software developers determine safety of their code. That's all I have for you today. Thank you all for listening, and I'd be happy to take any questions if you have any. Thank you.
Oh, okay, perfect. Thank you so much for a great talk.
Right.
So now, yeah. So now, if there are any questions, actually, we can jump right into the author discussion period, where we can ask questions to all the authors, including Zach. So I don't know. I guess Zach, maybe you can stop sharing your screen, and for all the other presenters, if you want to turn on your camera, you can we can have a nice discussion. There's one one question for Zach from Professor Lee. However, did you consider meltdown attack and getting secrets from registers rather than from just memory? So have you considered other attacks?
Yeah, great. Currently, we are just looking at the Spectre family as we think that they are kind of easier to analyze at this state. And we also have considered move operations that go from memory, or sorry, from register to memory as well. But currently for the scope of our project, we were just focused on memory load operations and specifically moving from memory into the registers.
Yeah.
So thank you for the question.
I'm not sure if you can hear my audio.
Yes, we can. Yes.
Okay, so this is Ruby Lee from Princeton. So I was just looking at your autonomous slide, and you say if it is from the same memory address, then it should be okay. But exactly the meltdown attack would be from the same memory address. So be careful. When you're saying memory address, you should go into another state and check if it's possibly meltdown, okay? And I think the other question was, you said you go into a state when you see a memory address, which I presume is, getting the secret on the speculative attack for Spectre. Well, be careful, because you could also get from floating point register or, those load buffers and, from system registers. So it's not always getting from a memory address. But otherwise, I thought this was interesting work and seems promising that you might be able to learn new attacks, okay, and check whether they go into vulnerable states or not. Thank you.
Okay, great. By the way, this might be a good time to reintroduce Professor Ruby Lee, who's one of the co-organizers, and Professor Larry Shi, who is another co-organizer of the workshop. So really cool. We have, and yeah, is there any questions from the audience? Feel free to type them. I did have one question following up on the prior question for Sylvia. You mentioned, Sylvia, that there's some hardware attacks that you observed first, and then they became software attacks. Do you have examples of what you mean by that?
Yeah, probably one of the first computer-based attacks was actually a hardware attack. And I have it in my paper. But yes, one of the first computer-based attacks period was a little toy that they created. Let's say at CERN. No, it wasn't at CERN. But it was a hardware attack, and that was pretty much the first computer attack. And then later we saw software versions of the same attack.
Okay, I see. Okay, that's really cool that there's this progression from hardware to software, if we can observe it. I did actually have also one question for Zach. In your example, there was like a no-op that you were jumping into after the Spectre attack. Was that just part of the sample code that you had, or is that a no-op that was inserted by the processor after it figured out that it has to exit the transient execution?
Yeah, I'm pretty sure that no-op was added after the fact. Yeah, there's actually no explicit no operations in the code. So that was added.
I see. Interesting. So that can be a flag that something has ended, and then you can resume. Okay, all right, sounds really good. And I don't know. There's so the middle talk actually was also quite interesting about the deep neural networks. So if I understand, so from Yueji, one of the things that you do is you use some onboard memory to hide the memory traces, if I understood it correctly.
Yes.
And have you evaluated sort of the trade-offs of of the size of the onboard memory versus how many different attacks you could defend? Because that seems like an interesting trade-off that bigger onboard buffer might kind of.
Yes, the size of the buffer is definitely an important issue. we have some reference code. The on-chip size, the global buffer, the original buffer is about 500 kilobyte. And currently we set our buffer to less than 64 kilobytes. So I think it is a good trade-off. And also if we divide more sublayers, in each sublayers, there will be a smaller portion to be stored into the buffer. So that is also a thing to discuss. We will do this in the future work.
Actually, do you have some algorithm or heuristic for when you use the on-chip memory versus letting it go out to regular memory?
Sorry, can you?
Do you just put every memory right into this on-chip memory, or is there some algorithm for when you would store it on chip versus send it off chip?
Yes. In our thread model, all the weights and feature maps will be read into the external memory. So I think all these operations have the access pattern on the memory.
Okay.
Okay, great. So yeah, I think we've run our course of the work in progress session. So we will have a short break until 12 p.m. noon Eastern time, about 8 minutes, and Professor Larry Shi will be taking over as the host for the session 2, and of course Professor Lee is here. So yeah, so please hang out. You can keep typing questions if you have them. The panelists should still see them until we switch the new session. So otherwise, Larry will be taking over soon to continue the workshop. So thanks to everybody who's here so far, and we'll be back in about 6-7 minutes.
Yeah, and I also wanted to add that I'm glad we had this work in progress session, because these are all interesting work, and I do encourage all of you to send in your early ideas and hopefully maybe get some feedback on it as you continue this work. So thank you, Jakub, and all the speakers.
Great. So yeah, and like Professor Lee said, you can start thinking about submitting your work to HASP 2022. So it's never too early. So anyway, so I will be off for a little bit, and then Larry will take over.
The first one is the presenter will be Haonan Li. And the title is Novel Memory Management for RISC-V Enclaves. And Haonan received his bachelor's degree from Southern University Science of Technology this year. He works as a research assistant in Compass Lab, advised by Professor Fengwei Zhang and then Zhen Yuning. His research focus is on system security and the trusted execution environment. And he's currently looking for PhD opportunities. So because the connection issue he has, so we'll play. Let me audio, the video, and post it on YouTube. So let me see. Well, Jakub, do you want to share your screen, the video? I connect to YouTube, but it seems like still connecting. I don't know what's the issue.
Oh, okay, sure. I can. I think I can do that. Okay. Can you see my screen?
Okay, thanks so much. Yeah.
Hello, everyone. Welcome to my talk.
Yes.
I'm Haonan Li from Southern University of Science and Technology. This work is collaborated with Wei Jie, Mingde, Hong Yi, Zhen Yu, He Ming, and Hong Wei. So today I will introduce our work, HASP, a novel memory management for RISC-V enclaves. Recent TEs on RISC-V usually meet two limitations. First, their concrete enclave members is usually restricted. Second, some features like memory request is still limited. These limitations are usually brought by their memory protection mechanism. Let's take the physical memory protection, or PMP, as example. The PMP is a standard hardware component for RISC-V, so lots of TEs rely on PMP to protect their enclave memory. So PMP can configure like accessibilities for contiguous memory regions. When CPU turns on to the host OS, suppose there are n enclaves, it will need like n+1 PMP entries, configure this amount of memory regions for each enclave to protect each enclave. And for when one CPU turns to the enclave, say enclave 1, it only needs like one PMP entry to cover the enclave memory. So the PMP is really powerful and handy, but it has a limited number of entries. From RISC-V standard, it can only support at most 16 entries. Therefore, here comes the first limitation. The number of enclaves is actually limited by the number of PMP entries. To overcome this limitation, a straightforward way is using one PMP entry to cover the whole enclaves like this. This way, no matter how many enclaves there is, we always require only one PMP entry to protect all enclaves. The shortage may be the useless sandwiches. We call these sandwiches memory between enclaves. It cannot be used by host OS, and it can only use for enclaves in future. So, but we think comparing to the larger amount of the whole memory, this memory of RISC is successful. The second limitation is a bit more complicated. If enclave 1 needs want to use more memory, say just something like it will need an extra 4 blocks in their runtime. So due to the limitation of PMP, the new memory region can be only located to its adjacent areas. So this means the request of memory requests, the result of the request and not always give the same. For example, in this case, all things goes well. You can directly put this 4 blocks to the adjacent area and request will succeed. But if in another case, you will see the enclave 2 use a bit more memory than before. So in this case, this sandwich area is not enough for 4 blocks. It can only allocate like 3 blocks. So you will see that this is the limitation, that memory request depends on other usage. If enclave 2 use more memory, but it affects enclave 1 cannot finish the request. It's not really wired. And here is the limitation 2. The memory request is limited. To solve this challenge, we introduce memory migration. It means to move memory to another location. Continue to our last example. In this example, we can firstly allocate like 3 blocks instead of 4. But with the help of memory migration, we can like migrate the next enclave 2's memory to another side as this, and make room for the last one. So you will see we can finish the memory allocation. And let's talk about the time complexity of the allocation algorithm based on migration. So let's consider the worst case. Suppose there are n enclaves and it requires like m blocks, and all enclaves are aligned closely. So in this case, if enclave 1 still needs 4 blocks, it will need like 4 times 2 migration, like this. Okay, 4, 8 migrations. So it will cause a relatively very high big overhead if not acceptable. To reduce the overhead, HASP allows fragmentation. It means we allow enclave to have multiple fragments. Let's recall how we use PMP to protect memory. Note if that the CPU runs on the enclave 1, we only need one single PMP to restrict the enclave 1 to be only used if on memory. So in this case, we can make full use of PMP entries and directly put the requirement to another sufficient free space. So we use an extra PMP entry to finish the memory request. So it's very easy, very directly. Allow fragmentations and make full use of PMP entries. Still, there is another situation. Because the PMP entries is still limited, as we mentioned before, when the PMP entries runs out, we introduce the smallest fragment migration. It means we will firstly find the smallest fragment of enclave 1 and move 1 to another free space and to finish migration. There is when PMP entries run out, they migrate the smallest fragment to another free space, finish allocation. Still, there is it a final case? You will see, in this case, the largest free space has only 3 blocks, and its smallest fragment is only 2. Has 2 blocks and only 3. So you cannot just migrate. Make no sense. So in this case, we introduce a memory compaction. It means we will scan each blocks being allocated, memory blocks to be allocated, and move it to the left as possible. So in this way, we can like make the largest free space on the other side, on the right side. So but you will see, although we do make the largest free space, we cannot simply put these 4 blocks to this area because it will introduce another fragment. We have said we have only 3 fragments to use. And so maybe an ultimate solution is to performing the compaction along with like merging fragmentations. It is also one of our future work. So now let's recall the whole procedure of the memory request. First, we will check if there is adjacent memory space. If true, then we directly expand previous one to finish the location. Otherwise, we will estimate if there are 3 PMP entries allocated to a new fragment or perform migration. And finally, considering the compaction. We evaluate HASP from 2 aspects: memory utilization and performance. For the memory utilization, it is measured by the ratio of used to be the total memory or the used to the memory pool. We evaluate HASP in different size of memory pool for different numbers of enclaves, and the result shows that in any HASP can improve by like 1.5 times to 5 times. These figures use the performance of memory allocation due to the lack of optimization, HASP is much slower than Linux allocation algorithm. But you will see the time is relatively small. So you see it was for 32 megabytes, it requires like smaller than 10 power of 8 cycles. So it is relatively small for the whole execution time. And the trend you see is linear. So to deal with the overhead is reasonable. And the turning point is 8 megabytes. It is also the size of our the smallest unit for allocation and migration. As for the memory migration, its overhead is basically proportional to the size to be migrated. And as for the compaction, the time of compaction varies for memory pool and the migrated partitions. Typically, in our experimental memory pool with like 7, 6, 8 megabytes, it will take like about 10 seconds to perform a compaction. So we should reduce the number of compaction as possible. So in conclusion, we propose a solution for memory allocation enclaves to overcome the limitations due to current memory protection mechanism like PMP. So with HASP's help, we believe the enclave application can use memory as native applications. And besides, we only relies on RISC-V standard hardware. And the overhead is relatively low. We also open source our code to help further research at here.
Well, thanks for the presentation. So since it's a video, not sure how to handle the questions, but if you have questions, I can forward to the authors, and hopefully they will respond. So and then we can move to the next presentation. The presenter will be Kuta Yoshida. Kuta is currently a doctoral student in Ritsumeikan University in Japan. He's interested in machine learning and hardware security. And his the presentation is about towards trusted IoT sensing systems, implementing PAF as a secure key generator for root of trust and the message authentication code.
Hello.
Yeah.
You hear me?
Yeah, you can.
Okay. I will share my screen.
Please go ahead. Thanks.
Can you see me? My screen. Hello?
Yes, we can see and hear you.
Okay. Thank you. Okay. Thank you for the introduction. My name is Kota Yoshida from Ritsumeikan University in Japan. I would like to talk about our study towards trusted IoT sensing systems, implementing PAF as a secure key generator for root of trust and message authentication code. And first, IoT sensing system creates various value by analyzing big data that acquired by huge number of IoT devices, where sensor data should be trustworthy in IoT sensing systems. Here, trustworthy means that acquired by correct device and correct sensor, and the sensor data is not tampered with. We assume the IoT device illustrated here This system is a collection of IoT sensing devices composed of a main device and subordinate sensors. The subordinate sensor acquires data and the main device aggregates this data and transmits it to a host server. It is similar to the modular structure in this picture. The main board includes a CPU, and the camera sensor is connected to the main board with a flexible cable. These IoT sensing systems face various threats. There is a risk of tampering with the sensor data, and adversaries may spoof the device and sensor and send fake sensor data. So we aim to take measures these threats to trusted IoT sensing systems. Previous studies focus security between the IoT device and host server. On the other hand, we consider that an adversary may access the IoT device physically, and then the modular architecture of the IoT sensing device faces additional threats. In this study, we also consider an internal security of the IoT sensing device, that is security between the subordinate sensor and the main device. We apply PAF and TE and remote attestation to protect between the main device to the host server. And we apply PAF and message authentication code to protect between the subordinate sensors and the main device. Next, we would like to talk about preliminaries and then introduce our proposal. First, I introduce TE and Keystone. TE provides an isolated memory space from untrusted OS and other enclaves. And then the enclave is protected from memory tampering. Keystone is an open framework to develop customized TE and RISC-V CPU. Second, I introduce remote attestation. Remote attestation is a protocol to verify integrity of the device and software. Remote attestation uses two public key pairs. One is the device key from root of trust, and the other is generated by device secret key and SM hash. Software hash and SM public key are signed by these keys. Verifier receives these certificates and public keys and as attestation reports and verifies these certificates. Finally, I introduce the physical unclonable function. PAF uses physical variables to generate device-specific values, and the variations cannot be cloned. The value may contain an error, so use a fuzzy extractor to fix the error. Typical PAF usage is a seed of encryption key, and so we use PAF as a secure key generator. From this slide, I introduce our trusted IoT sensing system. We assume the IoT sensing system illustrated here. The main device receives sensor data acquired by the subordinate sensor. The main device transmits the sensor data to the host server. As I said so far, the sensor data faces various threats. First, we introduce a security between the main device to the host server. We utilize a TE to protect applications that acquire sensor data and transmit it to server. In this study, we use Keystone to develop TE application on RISC-V CPU. Enclave application is executed in isolated memory space from untrusted OS. So adversaries cannot tamper with the sensor data in enclave memory space. Keystone does not provide an implementation of the root of trust, and then we implement PAF as a root of trust. we expect the path performs as a secure key storage. The path generates device public key pair for keystone. Next, we apply remote attestation to verify the main device integrity and protect communication with the host server. To begin with, it is necessary to distribute the device public key to the host server. The device vendor observes the device public key in manufacturing process and creates the certificates. And the host server receives the device public key and the host server performs remote attestation and verifies the correctness of the main device and software. The secure channel is established between the host server and the enclave. So the sensor data can be protected between the enclave and the host server. Here, I summarize the security of the part of enclave to host server, which is the first half. TE and secure channel protects the sensor data integrity, and path generated key and remote attestation protect device and software authenticity. However, sensor data is variable between the subordinate sensor and enclave because Keystone does not provide secure access to peripheral sensors. The subordinate sensor is not verified. The sensor data bus is unprotected, and sensor data goes through the untrusted OS. So next, we take measures these threats. We also implement path into the subordinate sensor. This path generates a shared key from the path response. We add message authentication code to sensor data by using the shared key. Enclave application verifies received sensor data by using MAC. Here, we required a way to displace the shared key from the subordinate sensor to the enclave. So the sensor vendor collects some challenge and shared key pair before the sensor shipping. And the sensor vendor creates the challenge and shared key database for each sensor. And the device vendor receives the challenge and key database corresponding to the subordinate sensor from the sensor vendor. The sensor vendor establishes a secure channel to the device with remote attestation. And the device vendor updates the challenge and shared key pair to the device. The shared key is encrypted and stored in the main device. The enclave verifies the sensor data by using MAC and the shared key. Here, I summarize the security of the part of enclave to host server. Path generated key and MAC protected the sensor data integrity and authenticity of the subordinate sensor. When the sensor data is tampered with, the enclave failed to verify the MAC. And when the subordinate sensor is replaced with different sensor, path is the sensor path in the sensor generates different shared key from the challenge, and the enclave also failed to verify the MAC. We demonstrated our trusted IoT sensing system. This is the implementation result. In the main device, utilization of the PG path and fuzzy extractor circuit is quite small than RISC-V CPU. In the subordinate sensor, we assume CMOS image sensor path and simulated by Raspberry Pi. In the future, we will develop a hardware implementation of the CMOS image sensor path and the MAC circuits. This is the screen of our demonstration system. Left side is the normal condition, no tampering and no spoofing, so we can take a picture. Right side is connecting incorrect device and raises error. So this is summary of our presentation. Previous studies focus security between the IoT device and the host server. We also consider an internal security of the IoT sensing device. We apply a PUF and TE and remote attestation to protect between the main device to the host server. And we apply a PUF and MAC to protect between the subordinate sensor and the main device. Thank you for your attention.
Thanks so much. And we have time for questions. And any question from the audience for Kuta?
Hi. Hello?
So yeah, so I just asked if anyone has questions. So I can share with you. So if nobody has question, and I have a question about the fuzzy extractor. So it works very well. What is the bit error it can tolerate? I mean, in terms of the if there is any the error in the fuzzy extractor used.
It is how we correct the error.
I mean the what kind of the error that like percentage or any kind of the error kind of can be tolerated by the fuzzy extractor in this because there are other ways to implement the error correction, right? That is there any trade-off between the number of bits for error tolerated versus the overhead or
we in this study we are using read-marker codes to correct the error in fuzzy extractor, and we can change the error correction code to other methods, or we are using read-marker 1.4, but we can change the parameters. So so we should select we can select the error correction codes to the implemented PUF.
Yeah. Oh, and so, yeah. So there's one question from the audience. So, so I just posted here. So does this protect PIs on the device as well, collected from the sensors?
Sorry, I can't understand the PII. What's that this mean?
The personal identification information. I think it perhaps means if the sensor is like a camera or a fingerprint sensor, you know, that basically can collect personal identification information like a iris scan, or you know that the sensors can capture the information that can be used to uniquely identify a person.
Okay. So the sensor have a path, and the shared key corresponding to the sensor. The sensor is sorry. The device vendor knows what the device has what sensor. So
Yeah, perhaps I think the question is if the such personal identification information, how it's protected, right? I know the integrity, the MAC, I think perhaps just talk about the privacy from that perspective.
Privacy of the sensor data is not in purpose in this slide. And we can protect the secretary of the sensor data. So we must use shared key encryption instead of the MAC.
Yes. Okay, because of time, let's thanks for the speaker, and thanks a lot. So we'll move to the next presentation. Thanks so much.
Thank you so much.
Thanks so much, Kuda. So the next presentation is on lessons learned from blockchain applications of trusted execution environment and the implications for future research. I will let the speaker himself to introduce. Rami, now you can share your screen.
Please unmute yourself. We cannot hear you.
Hi, sorry.
Thank you. Now it's fine.
Yeah, so hi everyone. I'm Rabimba Koranjai. I'm right now a student at University of Houston. I'm doing my PhD under Dr. Shi, and this is a joint work between everybody in the slide. So me, Dr. Shi, Dr. Lei, Dr. Lin, Dr. Fengwei, and Dr. Gao. So let's, without further ado, let's dig a little bit about what exactly we learned when we looked at the applications of trusted execution environment in blockchain applications, what people are doing, and some of the challenges we found out when we tried to do a few things on our own. So first, a little bit on how the paper is kind of laid out. So the nature of the study is, first we look into what the problems is, where the blockchain-based financial applications are being used, the security implications and threat factors, more necessarily like how you can actually attack the trusted execution environment, as well as how you can actually look, attack some of the threat factors of the blockchain-based applications. Then we look into the execution guarantees, what trusted execution environment provides us, the commercial platforms right now available to for us to actually use and exploit, and then the limitations and some of the future research and recommendation. So first, a little bit about background of the blockchain applications. Where is it right now used, or where it is being used or kind of exploding? So there are broadly three categories I'm going to talk about today. There are way more, but these three kind of encapsulate most of them. So first, the financial incentives. So it is being used a lot in different financial categories. For example, a marketplace for NFT. Some of you probably have seen NFT prices going up and down. So these are like assets. It can be pictures, it can be arts, or any of those kinds. And the marketplace kind of provides us a way to kind of track it, sell it, and all those things. And these are actually built on blockchains, on certain guarantees blockchain provides on different kind of places. So financial guarantee is one of them. The other two are broadly used, for example, cryptocurrency exchanges like Binance, Coinbase, and then there are cross-geography payments, which the banks and everybody is exploring. That can this be used to kind of explore cross-geography or cross-country payments, and what are the benefits, pros and cons, and all of that. Then comes the identity part. We have already seen in our previous presentation, there is a huge push in the personal identity management side, but blockchain specifically is being used by that because of certain guarantees provides, and because of certain promises, for example, anonymity and all this kind of stuff. The other one is a voting mechanism. So it has always been a kind of like ongoing research topic that can we use blockchain-based systems for voting and management. Does it provide us the integrity guarantee we need for a voting system? And what kind of attacks which right now are feasible in certain voting systems, for example, the star vote system of Texas maybe, or something like that, are those still applicable or valid concerns for blockchain-based systems? So that's an ongoing research topic, and people have been working on that. When we move to e-commerce platforms, there are things like supply chain tracking, actually tracking where your things are going. Also on the field of like actually tracking the integrity of those products. For example, you might have a medicine, if it is the right medicine reaching you, or is it a fake? Can you track those medicine, or like all of these things throughout its lifetime? So these things are being explored. That does the auditing capability of blockchain and the integrity protection give you that kind of capability. Then there are original content creation and also micro payment based economy, which is kind of like trying to see that, okay, can there be like an alternate way of, instead of going for advertisement based product consumption or the web asset consumption, can there be like an alternate way of providing micropayments based on certain activities you do on your browser or something like that? So how does trusted execution environment fits in it? Right now, how our computer works is that we have a too big trusted computing base. For example, any device the blockchain will run on, or anything we do runs on, is a whole computer operating system, and there are two big surfaces of attack. TEE, trusted execution environments, try to prevent that by giving you a small attack surface, a very small attack vector, which is supposed to be very secure and isolated from your normal computing instance, so that you have certain computing guarantees, and they're mostly backed by hardware and with certain vendors, which we'll go through in the next slide. So certain applications in blockchain can leverage that, and actually are leveraging it for these specific guarantees. For example, Fast PFT uses trusted execution environment to store its cryptographic keys and secrets to kind of protect the integrity and use the same kind of guarantee TE provides, and not build something on their own. Poet by Intel tries to replace the proof of luck using tries to replace the proof of work using proof of luck, and how they do that is actually have it generate a random time, and use the random time generator inside trusted execution environments enclave to do that. Obscura, another project, another paper actually tries to correct the mixing operations, and they try to do that keeping the private keys and the logs inside TE. Very similarly, there have been implementations of whole wallets, it can be a Bitcoin wallet, or it can also be like a Ethereum wallet, or any kind of wallets. So lightweight wallet have been implemented inside TrustZone. So TrustZone is something ARM came up with. So you can actually have these inside certain mobile computing devices. So these were some of the use cases, how trusted execution environment fits in. Now, as we have seen, these are very interesting use cases, and certain projects are already utilizing it. But when we actually look at these use cases, we also have to look at which devices right now we actually can use it, not as a theoretical way, but actually in a practical way. So the commercial hardwares which are available to us right now is Intel SGX, AMD Secure Enclave, ARM Trust Zone, and FPGA-based trusted execution environments. So Intel provides its own secure enclave that's called Intel SGX. It has two versions right now, version 1 and version 2. Each of them provides certain integrated protections and has certain limitations. AMD similarly has a secure enclave implementation of it, which also does the same thing as Intel, except it gives us a few more freedom with the hardware where you can do it. Intel's SGX mostly is based on server side, so mostly it's available for servers, not always in consumer devices unless you go for very specific consumer device. AMD is a little bit lenient. In that case, it is available for more devices. ARM has its own trust zone implementation where you can actually implement something inside trust zone and it will run inside that. It's a little bit different than SGX and Secure Enclave, but you still can have that protection and implement something there. FPGA-based TEs are very specific to what they do because of the nature of FPGA, but they also are being utilized for certain applications. So when we look at the properties of this commercial trusted execution environment and started to look at it, so we found a few concerns. So the remote attestations often depend on a centralized managed services. When it comes to a blockchain application, that's probably not a good idea for or a good use case for most of these. Each platform targets a different application sector. For example, Intel's server implementation, that's completely, mostly it's for servers and it's not really for commercial or portable devices as well. Hardware and software support for these execution, like these environments are not clearly defined. And their scopes are not defined as well. So that brings us an interesting problem is that even though we know that where these are used, not all projects can utilize that because those supports are not available in all of the devices, even though it's supported in the stack level. For FPGA, it offers a very unique solution because those are literally differs based on device to device. So that's not something even we can actually broadly benchmark or compare. AMD provides us a little bit more flexibility because of the hardware support they have, and also the software kind of works out of the box for those hardware, like supported hardwares. But even then, for commercial devices, it has to be, it still is a very like small number of devices where it is supported. So even if you try to build a solution right now, there's a very less number of people where you can use that. So so starting with a little bit conscious of the time, I'll look at the challenges and attacks. So the primary problem we faced is that the reliance on centralized structure that literally kind of takes away the like decentralized structure we had for blockchain. There are no economy-based security models for any of the trusted execution environments we saw. The line between hardware and software of these like TE models differs a lot, and there is no clear distinction. One primary example comes to mind is the ARM Trust Zone, where mostly you have to build it on kind of the VM side to actually test it, but then you have to know which devices, which OEMs will support that. And also there is no good way to detect and like respond to a compromised TE. For example, if like there have been attacks coming out for Intel SGX in kind of a steady stream, and there is no easy way to detect and mitigate them because this is hardware backed, and what you have built is like right there. We like cannot control that. So some of the opportunities and future research directions we propose is that we really need some of the security primitives. Two of the things we kind of propose or that comes to mind is that we really need a trusted and accurate wall-time clock. This can be implemented inside Secure Enclave, and a lot of projects and things depend on it. For example, Google's NoSQL and all these things, they depend on it. And right now, everything falls back to the NTP and how it gets a time. So having a accurate wall time clock is a probably good idea. And we also need to have some kind of support for detection of continuous state for hardware TEs. So those are the two things we thought of. The other things we should look at is the decentralized identity management inside TE so that the attestation becomes easier, and then also programmability, security, and proper standardized support for the TEs. So in conclusion, we looked at like what the applications are for blockchain-based, T-based blockchain applications, where these are being used, some of the limitations, and how we can actually kind of broaden it. So the lessons learned from these use cases gives us a potential direction, and we hope to kind of pursue that in future cases. And that concludes my talk. I'm ready to take any questions you might have. Thank you.
Okay, because of the time, I think maybe I don't have time for questions. If you have any questions, you can send email. I can forward to the presenter. So let's move to the last presentation. It's invited talk. We're very fortunate to have presenters from ARM to talk about the new design and the ARM confidential computing. This is a great opportunity to know more what behind the ARM CCA. We have the expert here, and we're presented by Mark Knight. And Mark has worked for more than 30 years in the development of technology products, and with over 20 years specializing in security and cryptography. Before joining ARM, he and Microsoft and Grow Vayner Technology.
Hi, this is Jack. I think we lost the audio.
Yeah, I think we lost Larry. Shall I start?
Larry. Larry, can you hear us?
Hello?
Yeah, we lost the audio.
Yes, I can. You can hear me? No?
A little bit. So if it's okay, maybe Mark and Gareth can start.
Perfect, I will do. So I don't know if Larry was able to introduce Gareth, so I'll do that. So I'm Mark, and I'm joined today by Gareth Stockwell, who's a senior principal architect at ARM, where he focuses on the development of security architectures. So he's on the line as well, and we'll be sharing the presentation. And thank you very much for the invitation to speak at today's workshop. There we go. So we announced our confidential compute architecture in March of this year, and we publicly released the technical specifications in June at an event with Linaro to help progress the software and enablement process. We expect real-world devices, chips are going to probably be 2 to 3 years away. ARM confidential compute architecture is an isolation technology that builds on the foundations of Trust Zone that we've just heard about to protect data in use. And this work has really been driven by the expanding need to ensure privacy and security while allowing data to be harnessed in new ways. So, for example, to support innovations powered by artificial intelligence and the rise of cloud computing. So confidential computing is the concept of hardware-enforced protection for data in use, really protecting from privileged software and hardware agents. As an example, this can allow virtual machines to run on a shared computer without the entity that manages the underlying computer having any access to your code or your data. And this is typically achieved using one or more isolation technologies that restrict access to code, processor state, and application data within a system. And the ARM architecture has supported confidential computing in some form or other since 2003, when we first released TrustZone. And TrustZone has now shipped in billions of devices. Since then, we've been on a journey to enhance the isolation technologies we offer to extend confidential computing to an increasing breadth of workloads. So since 2003, in ARM v7, we introduced exception level 2, EL2, and stage 2 translation to improve security and performance with hypervisors. More recently, in the architecture 8.4, we added secure EL2, which enables you to virtualize the secure world. And now, bang up to date in ARM v9a with the ARM confidential compute architecture, we have the next step in that journey to extend hardware-backed secure processing really to all software workloads. And the instruction set feature that supports this architecture is called the Realm Management extension. So before we dive into the detail, a little on our vision. So we really believe that secure computing needs to be accessible to all developers. We want to extend the kind of high trust environments that have really mainly been only accessible to silicon vendors and OEMs using TrustZone to all developers. And we call these new high trust environments realms. This architecture provides a strong protection between mutually distrusting workloads and strong protection against a compromised rich operating system such as Linux or a normal world hypervisor. And for the first time with this architecture extension, we also protect realmed workloads from applications running in the secure world. Attestation is also supported, so a realm can verify trust in the platform or device and present an attestation record to underlying parties so that can be independently verified. So I'll show a quick picture here to show how we deliver on this vision. So realms here are shown in yellow, and they're the new confidential compute environment whose memory cannot be accessed by a system hypervisor, TrustZone applications, or indeed other realms. A platform can support many realms at the same time, really just limited by the performance and total available memory on the system. Realms can be created and removed dynamically as required, and the resources assigned to them, specifically memory, can be increased or reduced on demand. And this hardware-based protection includes protection from virtually everything on this diagram, apart from the very lowest level of firmware or monitor. Specifically, applications running in a realm are protected from a hypervisor that is responsible for scheduling a realm, but no longer has access to a realm's data. And as I've previously mentioned, realms are also protected from the secure world too. The monitor shown in blue in this diagram now runs within its own physical address space. The architecture requires that external memory is encrypted to protect against cold boot attacks, and this is covered by a specification for a memory protection engine as part of the memory controller. So before I hand over to Gareth to go into the architecture in a bit more detail, I'll just take a moment to look at the threat model we've used in building this architecture. So on the left, our primary focus is the confidentiality and integrity of workloads running within a realm. One area where realms are different to TrustZone is that realms do not guarantee availability. So a normal world hypervisor is still responsible for scheduling a realm. And then on the right, to be fully secure from side channel attacks, the protection relies really on a combination of the architecture and the workload you're running in a realm. So for example, a realmed virtual machine kernel still needs to support standard protections for side channel attacks like Spectre and Meltdown. Gareth.
Thanks, Mark. Sorry, just look at the mute button. Thank you. So I'd like to go into a bit more detail now on the architecture, and in particular, how the combination of hardware, architecture features, and firmware come together to deliver confidential compute on ARM. So to start with, here's a diagram of a typical software stack on an ARM v8.4 platform. And as Mark has already summarized, there are a number of mechanisms that can be used to isolate software components on this architecture. And they include the separation between the secure and the non-secure states. So in this diagram, we have a thick dotted line indicating that boundary. And each of those two security states have their own associated physical address spaces. And there's a table at the bottom of the slide that summarizes the access rules to those physical address spaces. And the key property of this is that secure software can prevent non-secure software from accessing secure physical memory. And so the result is that we have two worlds, or in other words, we've virtualized a processor into two virtual processors, secure and non-secure, with the secure side being strictly more privileged than the non-secure side. And switching between these two security states, or two worlds, is performed by the monitor component that runs at EL3. And so in this architecture, the monitor has two properties. It's both the most privileged component on the system, and it's also part of the secure state. And we'll see in a moment how that picture changes when we introduce the ARM CCA hardware architecture. So alongside trust zone, the other isolation mechanism that we'll talk about is page table based isolation. And so within a security state, ARMv8.4 allows access to a component's memory to be protected or controlled using page tables. And optionally, there are two stages of translation that can be applied with stages 1 and stages 2, with stage 2 being managed by the hypervisor or the secure partition monitor, both of which execute at EL2 in the respective security states. Go to the next slide, please, Mark. So in ARM CCA, we're introducing a supplement to the ARM 9.2 architecture, which is called the Realm Management Extension. And RME consists broadly of two features. First of all, it provides a new execution environment for confidential compute workloads. And as explained previously, this is aiming to serve a different user base from Trust Zone. And so rather than being an environment for hosting platform services, realms are intended to combine the generic compute platform that third-party developers expect with additional privacy and security guarantees. And we believe this is a great fit for rising demands in terms of data privacy, and which are evidenced by a number of different standards and a number of different activities. The second feature that CCA and RME in particular deliver is an architected mechanism for dynamically moving memory between physical address spaces. And in CCA, this is leveraged to avoid the need for any arbitrary limits on the number and the size of realms that can be hosted on a given platform. So in CCA, availability of physical memory is the only constraint on the set of realms or the set of confidential compute workloads which can be instantiated. But actually, this dynamic memory management feature is not specific to the realm world. It can also be used to dynamically allocate memory to tasks running in the secure state. So it has benefits for existing trust zone systems as well. But in this presentation, we'll focus on its usage in CCA. We can move on to the next, please, Mark. Thanks. So let's have a look in a bit more detail at the CCA hardware architecture. And if we compare the diagram on this slide to the one I showed a couple of slides ago, the first obvious addition is the realm security state in yellow on the left of the diagram. This provides 3 exception levels, just the same as the non-secure security state. And the architecture of realm EL0 and realm EL1 is deliberately similar to the corresponding exception levels in the non-secure state. And this means that a workload can be easily migrated from running in a regular non-protected VM into a realm VM. And the second difference that you might spot on this diagram is that RME also adds another security state in addition to realm, which we call root. And we've moved EL3, previously in the secure state, now into its own root security state. And together with that new security state, we introduce a new physical address space. And that's the mechanism by which we isolate the monitor from all the other security states, including the secure state. And that in turn means that the owner of a confidential compute workload doesn't need to trust the software that's running in the secure state. So if we now look at how memory is managed and protected in this architecture, as I mentioned before, there's an architected mechanism for dynamically assigning memory to a physical address space, and that is that's controlled by software that's running in EL3. And the monitor software programs a granular protection table, and the access rules which are enforced by the granular protection check are summarized in the table at the bottom of this slide. an invalid access that violates those rules causes a new kind of fault, which we call a granular protection fault. And that's routed similarly to other existing fault types in the architecture. And so the granular protection check can really be thought of as an extension of the MMU that we already have, whereby once an access has been translated via either 1 or 2 stages to a physical address, then the processor consults the granular protection table, determines which physical address space the target memory lives in, and then based on that determines whether the requester has the permission to access that memory or not. And just like translations, the contents of the granular protection table can be cached in TLBs to improve performance. So we have this separation of physical address spaces. Within a physical address space, we still have isolation that's enforced using page tables, just like in the existing architecture. And in realm security state, we have a set of translation regimes, and they include one which allows software running at realm EL2 to enforce separation between realms. That software, as you can see on this diagram, is called the RMM, the Realm Management Monitor, and I'll speak a bit more about that on the next slide. In addition to mapping realms private code and data, we can also share memory between a realm and the non-secure state, and that allows the realm to communicate with the outside world, for example, via a non-secure device. Okay, yeah, Mark, can we go to the next, please? Thanks. So I've said a little about the hardware architecture that underpins CCA, but the full solution requires not only that, but also a set of firmware components, and they're summarized on this slide. And the reason that we've approached the design in this way is that it enables us to keep the hardware relatively simple and therefore easier to verify, and then to move the logic that's used to manage realms into software, which can then be inspected by third parties and verified. So working from the bottom of this slide upwards, we have the monitor that programs the GPT, as I mentioned previously. And then within the realm security state, the RMM executes at realm EL2. And although it executes at EL2, which is the same exception level as the hypervisor in the non-secure state, the RMM is deliberately not a hypervisor. And rather, it's a component that provides a set of services to the hypervisor, enabling the host to create and manage realms. So really, a way to think about the RMM is that it is a layer of indirection between the hypervisor and the underlying hardware. And so when the hypervisor makes a decision to, for example, allocate memory to a realm, then the manipulation of the architectural state that the hypervisor needs to do is indirected via the RMM. And this means that the policy for managing realms, including whether to schedule a vCPU, whether to allocate physical resources to a realm and which physical resources to allocate, all of that policy stays in the host hypervisor. The RMM doesn't contain any of that policy. It doesn't receive physical interrupts. It doesn't run a scheduler. It doesn't dynamically allocate memory. It simply provides a set of mechanisms to the hypervisor to enable it to enact the policies that it has. And it also, the RMM critically also enforces a set of security guarantees so that it prevents a buggy or a malicious hypervisor from violating the confidentiality or the integrity of a realm. Finally, the RMM exposes a set of ABIs, and which we specify in a firmware standard. And those include an interface that we call the realm services interface, which is presented to the realm. And that allows features including, it allows the realm to obtain an attestation report for itself, which I'll speak about on the next slide. And it also is used for managing sharing of memory with the host, as I mentioned previously. The other interface that the RMM exposes is called the realm management interface, and that's used by the hypervisor to manage realms, create and destroy them, allocate resources to them, and schedule them. So we'll come back in a few slides' time to talk about the specifications for these ABIs and the reference implementation that we're planning to deliver. So we could go to the next, please, Mark. So the combination of the hardware and the software functionality that I spoke about before can provide a protected environment for a confidential workload. But the key question is, how does a realm user know that their assets are really being protected? So for example, how does the user know that the protected environment that it's communicating with really is inside a realm and it's not running in a simulator that an attacker has access to, or that the protected environment is really running the software that the realm owner wants it to run? and that the realm owner is willing to trust. So in order to deal with those questions, the realm owner needs to establish initial trust in a realm. And to do this, we use attestation, and that can be defined as a process via which an entity, in this case the realm, produces some evidence about itself, which another party can use to determine whether to establish trust in that realm. And so in CCA, really that breaks down into two parts. First of all, a set of mechanisms that the architecture provides for generating an attestation report. And secondly, the process for validating the attestation report and deciding whether or not to trust the realm. So looking first at the attestation report side, the generation side, the firmware ABIs that I spoke about on the previous slide allow a realm to request an attestation report. And that includes a number of different pieces of evidence, including a set of measurement values that describe the platform and the firmware that's running on that platform, including the RMM and the monitor themselves. It also describes the realm's initial state, the code and data which was placed inside the realm when it was created, and how the realm was configured. And then optionally, the realm can also capture measurements during its own runtime. So for example, a bootloader inside the realm can measure the payload that it's loaded before it hands over control. And these measurements can also be included in the attestation report. And then finally, that report is cryptographically bound to the platform before it's returned via the realm to the realm owner. So how does the realm owner decide whether to trust that report? Well, it needs to validate that the signature matches one of a set of implementations of CCA that the realm owner is willing to trust. And it also needs to validate that the measurements match the expected software and the expected configuration. And rather than producing a one-size-fits-all solution to this, we think that the requirements for this validation process are likely to differ between markets and between ecosystems. But at the same time, there will be some common requirements, and those can benefit from generic solutions. And so the approach we're taking is to provide a set of components which can be used to build a verification service. And this is being provided through an open source project called Verizon, which is hosted inside the Confidential Compute Consortium. So with that, I'll hand back to Mark.
Thank you.
Presentation.
So today, without confidential computing, there's always a security trade-off in allowing a single device or to access data or applications from different vendors, or when mixing personal and corporate data. So on this slide, I'd like to take a moment to describe some example problems that confidential computing can help to solve in different markets. So in the mobile world, coexistence has historically been addressed with potentially invasive mobile device management, or indeed by sometimes requiring users to carry multiple mobile phones, multiple laptops. If we think about a vehicle's cabin, a car, a truck, there's often a complex relationship between vehicle ownership and many different users and stakeholders, and that's only going to grow. So in the future, stakeholders may include OEMs, leasing and insurance companies, entertainment suppliers, ride-hailing or courier delivery apps, and even smart city networks. Shared microprocessors are essential to reduce the cost and weight and to fit within the power budget. And there can really only ever be one display or dashboard that needs to be shared by all of these stakeholders in an automotive scenario. In the public cloud, we aim to help providers take more of what I call the invisible cloud infrastructure out of the data path, allowing providers to really move from a model where they will not access our data to one where they cannot access our data. Really, ARM CCA has been designed to support both attestation and isolation between workloads and different personas in all of these different markets. So a little about the resources we've released for ARM CCA to support the open source and research development communities and really to get everyone involved at an early stage. So all of these resources can be obtained now via the web page at the top of this slide. We have tools and hardware architecture manuals that have been publicly available since June. We had a joint ARM Linaro tech event in June, and all of the videos for that are online and free to get at as well. We also contributed the first open source software for the EL3 monitor to the Trusted Firmware project. And in due course, we plan to contribute an implementation of the RMM, the Remote Management Monitor. And while Silicon is likely to be a couple of years away, you can also get hold of a free software model, a fixed virtual platform, or FVP, which you can use to support software development and research now. So that takes me to the roadmap slide, a quick overview of the areas where we're still working. So to date, we've shared the hardware specifications for Realms. And they've really been, Realms today are best suited really for CPU-only workloads that run entirely within the processing element. The three areas that we're working on, completing the software architecture for Realms. So Gareth mentioned the RMM. We're still working towards the first public version of the specification and a reference implementation of an RMM. And we expect the spec for that to be released next year. We're developing a device assignment architecture that will allow off-CPU devices like accelerators to have DMA into Realm physical address space. And then memory encryption contexts, where we're looking to mitigate the risk of additional physical replay attacks by encrypting each Realm's memory with a separate ephemeral key. So those are some of the areas that we're working on next year. And then with one eye on the clock, here's a summary slide, and perhaps a great time to take a moment to look at any questions that have come in. I'm just going to stop sharing my screen so I can see the Q&A.
Thank you so much. I'm not sure if Larry's microphone is working yet or not, but yes, if there are any questions, that would be great. And I guess you can see the Q&A box. Should I read the questions, or do you want to just read them and answer?
Wondering whether Gareth had a chance to look at any while I was talking.
Maybe I'll read the.
That would be great, and then Gareth or I can jump in and answer them as
Yeah.
appropriate. Yeah.
Perfect. So there's a question: is the ID of the realm owner known, and if yes, at what level?
Gareth, do you want to have a go at that one?
So it's not. I mean, it's at an architectural level, no. However, we are planning to include in the architecture mechanisms to personalize a realm, such that, for example, a realm owner could take a generic image, so a virtual machine image, instantiate a realm with that, and then inject or include some of their own personalization data, which could include some type of ID which associates it with that realm owner. So not directly, but we plan to support binding of a realm to a particular owner.
Okay, perfect. Thank you. And we have another question about through what mechanisms should Realm users protect themselves from side channels? Is there any hardware support for the side channel defenses, I guess?
So ARM has gained a lot of experience over the past few years on side channels, including speculative execution related side channels. And we've introduced a number of measures into the architecture in recent versions, which apply to virtualization and to trust zone and can be used to counter these side channels. So we're continuing to research in this area and to ensure that any mitigations and mechanisms that we put in place are also applicable for Realm-based workloads.
Okay, perfect. Yeah, I guess everybody's worried about side channels these days, so it's an issue. All right, there was another question that I guess was answered, but just so everybody can hear it. Is there a support? I guess does remote attestation or the direct anonymous attestation, is it supported or implemented? And I guess you already answered this in the chat. The ARM CCA does not directly implement or mandate DAA, but the answer was you're investigating how the ARM CCA primitive could be used to support a direct anonymous attestation. That's really cool. So yeah, I don't know if there are any more questions from the audience. Okay, great. Well, this was really a really good talk. Oh, there's another question actually from Larry, I believe. Are there any devices in the market that support this architecture, or what's the timeline for devices that will be supporting this?
So there aren't any devices in the market yet. So that's something that our partners are working on. Typically, we expect it to take 2 to 3 years from when we release a major new architectural feature such as this to the first devices being available. So that's the sort of timeline we're looking at, 2 to 3 years, I think.
2 to 3 years. Okay, great. And actually, I have a sort of a follow-up question. A lot of us here are are researchers interested in testing things out or actually modifying it. Do you know, will there be any Gem 5 or other type of simulator that people can play with, if they want to test the features, or in the future maybe try to modify the features?
Not sure if Gareth can add anything, but you can definitely get hold of the fixed virtual platform model, and that's available on the website. So that's something that you could get hold of now.
Okay, perfect. I wasn't sure. And is this for Gem 5 or for another simulation?
No, so that's an architectural simulation. So it doesn't provide cycle accurate modeling, but it's a suitable platform for software development.
I see. Okay, perfect. So there's already something we can play around with and test things out. Okay, really good. Yeah, I don't know if there are any more questions from the audience or from any other or the other panelists. Okay, really good. So thank you so much again, Mark and Gareth, for this. This is really good to hear about actual industry implementations and not just research.
Thank you, and we'd love any feedback. Thank you.
Yeah,
thanks very much.
Yes, and yeah, exactly. So if anybody has some more questions or feedback, we can forward it to Gareth and Mark. There's not a paper associated with this invited presentation, but the names are listed on the webpage, and we can always forward the questions, and perhaps next year we'll have an update about the progress of the CCA and the implementations. Okay, great. So this concludes the trusted execution environments session. We will take a short break, and then we'll resume with the last session 3 on quantum computer security after the break at 1:30 p.m. Eastern, which is in 10 minutes. So and Mark kindly shared his email with everybody in the chat. So if you have questions, feel free to contact Mark. And so so after break we'll be jumping from classical computers to quantum computers. So please come back. All right, thanks everybody. We'll be resuming in 10 minutes. And I will just share our break slide, and so we'll see everybody soon. Recording. All right, so welcome back. Welcome to the session 3 of the HASP workshop, which will be talking about quantum computer security. And for this session, we modified the order slightly. So the first paper that will be presented is the short paper titled Quantum Circuit Obfuscation Methodology for Security and Privacy. And Akarshita, you can test sharing your slides. So Akarshita is a master's student in electrical engineering at Pennsylvania State University. She did her bachelor's in engineering from PES University, Bangalore, India, and her research interest is in hardware security and quantum circuits. So this is great to have you here. And we cannot hear you. I think you're muted.
Okay. Yes. Can you hear me now?
Yeah. Now it's perfect.
Thank you. Thank you for the introduction.
You should be able to. Yeah. No worries.
So, can you see my screen?
Yeah, it looks good. Yeah.
So, yep. Hello. So good afternoon, everyone. My name is Karshita Suresh, and I'll be presenting to you a talk on a quantum circuit obfuscation methodology for security and privacy. And my co-authors here are Abdullah Shaki and Mahbubul Alam and Professor Swarup Ghosh. This work is done by Pennsylvania State University in collaboration with IBM. So I will be happy to present to you this work. So I would like to begin with some of the quantum circuit preliminaries. So I would want to explain what each of these mean. So this is a quantum circuit and which is implementing an ELU OR function. And what is a quantum qubit? It is notated by the Ket notation, and it follows these three main laws, which is superposition, entanglement, and interference. And these laws are what it abides by. Superposition mainly means that two or more qubits can be they can be in the more than one output state at a time. Entanglement means if these two qubits are even physically distant, they can still give some information about the other qubit when one qubit is measured. And the third one is interference, where you have interference between the two qubits. And the next thing is a constant qubit, where initially all the qubit lines are reset to 0, and there is a use of NOT gate to make them input as 1. And the next one would be a quantum gate. A quantum gate looks something like this here, which represents a CX gate or a controlled NOT gate. These gates perform operations on the qubits for on the initial inputs to give you a certain kind of output. So this circuit here is implementing the ALU OR function. So you're going to get an OR circuit here. And finally, the M here depicts the measured qubit. A measured qubit is the one which is being measured for the final output. And of course, it can be greater than 1 qubit. In some circuits, all the qubits are measured. So this is some of the basics of quantum circuit. So now moving on, what is the motivation behind this paper? So there is a need for a secure compilation. First of all, why do we need compilation? Compilation translates the high-level quantum gates into machine level instructions, and this also resolves any connectivity constraints. So which are common in quantum circuits, and hence there's a need for a secure compilation, because sometimes compilations can add extra gates which will degrade performances in some NISQ computers where there is a lot of noise or there's a short lifetime for the qubits. And so adding extra gates would degrade the performance. And this in turn means that there is a need for a critical efficient compiler. That means your compiler needs to be efficient, and at the same time it has to be secure as well. There are several third-party compilers like PyTicket, which are more efficient than the existing compilers like Qiskit or Quilcy, but there is also a level of security that needs to be achieved while using these third-party compilers. And for example, if there is a quantum circuit which has critical information, like if it is being used for a power grid application or if it's being used for some machine learning application, then it contains a lot of sensitive information which is at a risk of stealing or a leakage, and hence they become critical and important IPs which need to be protected and securely compiled. Therefore, there is a need for secure compilation, and the solution for this is to use a technique or to develop a technique which can also take advantage of these compilers and at the same time be secure. In our model, we also look at what the adversarial capabilities can be. And so we assume that they have the access to the obfuscated netlist or the net circuit, and they can also perform any type of analysis on the circuit. However, there is a lack of an oracle model for the adversary. So what do I mean by oracle model? In traditional CMOS, there can be an reference model like a chip, which can be used for validating the results. But in our model, the adversary cannot have an oracle model because all the quantum qubits are implemented using microwave pulses, and hence there is a lack of an oracle model. So moving on to the threat model, we see that there is a vulnerable circuit which is being sent to the third-party compilers. And now we are going to add our dummy gate, which is highlighted here, into the circuit. And this is added at targeted location, and this is called logic obfuscation, which is the title of our paper. And then the circuit is being sent to the untrusted compiler for the attack model. Some of the risks are listed here. They can be counterfeiting, they can be reverse engineering, tampering of the circuit, they can be a Trojan insertion, and they can be a fault injection. So whenever our obfuscated circuit is sent to the untrusted compiler, there is a level of protection because now the actual original functionality is hidden from the adversary and it gets the corrupted circuit instead of the actual circuit. And after the compiled circuit is received, we remove the extra gates safely from the compiled circuit. And this is how the threat model is achieved. Also, one of the reasons why we choose on a type of gate or a particular type of gate called CX gate for the dummy gate is because as you can see, the circuit already has a lot of CX gates in the pre-compiled circuit, and that means choosing a dummy gate of the same or a similar type of CX gate will create a level of confusion for the adversary, and that's the reason why we choose that gate. Moving on, we look at a metric or a measure to quantify our obfuscation. So if you look at this slide, we see the same circuit from the previous slide, which we used for the threat model. And we see that when a dummy gate is inserted, so the initial output, it had to be 0. 0 is the correct output for the output state, and 1 is the wrong output. But if you look at the obfuscated circuit count, we see that the outputs have been reversed. We see that 1 is being shown as the correct output here. So that means that the output has been corrupted, and that means that there is a difference between the output for the original circuit and the obfuscated circuit, and this difference is being measured by a metric called total variational distance, and it's just the difference between the counts of the original and the obfuscated circuit, and it's expressed in percentage. So this is a statistical distance, which is a measure to quantify how much the circuit has been obfuscated. So if we look at the procedure, initially for the circuit, we add the barriers around all the CX gates, and we also add additional barriers other than for the dummy gates. This is done in order to create confusion for the adversary. Now they don't know which of the CX gates are the dummy gates versus which is already present in the original circuit. Later we add our dummy gates, we create this for the obfuscation. We also develop a metric for the targeted insertion of the CX gates. This is because, as you can see from the diagram, we see multiple gates are possible to be inserted in the circuit, and so there arises a question as to which position is the best for the TVD or the obfuscation. And so there is a metric developed for this particular problem, and we do a targeted insertion. And the last step would be deobfuscation of the compiled circuit. Some of the developed metrics include these. Some features like depth, which is how far the gate is from the output, a constant qubit, whether the qubit is being used as a constant qubit or a constant input, the number of control qubits. So the ones shown in dots here are the control qubits. That means that these qubits control the operation of this gate, and hence the value present on this qubit or the output of this qubit matters a lot. And the number of qubits in this path to the output qubit. So if we look at a path from that particular gate to the output, we see how many control qubits are present in that path. And also if the qubit is being used as a measured qubit. These features are not individually strong enough for obfuscation, and hence they're used as a metric in combination to create a better obfuscation, and detailed analysis is done in the paper for this targeted insertion of qubits. Moving on to the results, we see here that our developed metric 1 and 2 works better than most of the average TVD, which is selected randomly for the dummy gate position. And also we see that it is quite close enough to the best TVD possible for each of the 10 circuits on the x-axis. And so this graph shows that our metrics 1 and 2 perform better than the average TVD by almost 10%. So in summary, I would like to say that this paper talks about the need for secure compilation and how logic obfuscation can be used for this particular idea. And we also develop a heuristic metric for the insertion. We discuss the deobfuscation and reverse engineering in the paper. And we also discuss what could be the future work, which involves multiple gates insertion and other types of gates being used, and also using other type of statistical distance to quantify this obfuscation. And I would like to thank everyone for listening. And if you have any questions.
All right, perfect. Thank you so much for a really cool talk. So yeah, we have about 1 minute before we have to go to the next talk. And you can again type in your questions if you want. I did have one question about you insert the CNOT gates in the circuit, then it gets compiled. And then you mentioned that the inserted gates are sort of removed at the end. But my understanding is that the circuit gets compiled into a set of pulses that control the qubits. So how can you remove the added CNOT gates later?
So the microwave pulses are used to design the qubits in the industry or in the actual hardware. But when we are implementing this idea on a noisy model of the hardware, where we are trying to understand how the idea of obfuscation can actually help in securing the circuit even better. So the designer knows now the designer knows where the dummy gates have been inserted, but there is a level of confusion for the adversary, and also a lack of an oracle model with which it can validate its own results, and so it creates a level of it increases the efforts of the adversary to reverse engineer.
I see. All right, perfect. So yeah, this is great. And again, after the next talk, when the session ends, we'll have a short discussion period with the authors. So you can also have more questions there. And please, again, feel free to type away your questions in the chat box or the Q&A session. So now I guess to the last talk, maybe Alan can share his screen. And thank you for a nice talk. So the next presentation is again a short paper called Device and Locality Specific Fingerprinting of Shared NISQ Quantum Computers. And the presenter is Alan, who's a senior undergraduate student at Yale University. He's interested in quantum computing and security. He's part of the Yale undergraduate quantum computer club, and in general has been researching at the border of physics, math, EE, and CS. So he has a great background in quantum computers. And today he'll talk about the work on fingerprinting of quantum computers. So Alan, go ahead. And
right, thank you, Jakub. So let me share my screen. All right, I wonder if you could see it.
Yeah, it looks and sounds good.
Okay, awesome. So hi everyone, I'm Alan, I'm an undergrad at Yale. Today I'm here to present my work with Deng Chuwen and Professor Jakub Steffer on device and locality specific fingerprinting of shared NISQ quantum computers. So let us first start with the motivation. The following figure shows the number of qubits as it develops with regard to time in IBM superconducting architectures. As you see, from year 2019 to 2021, there has already been a quadrupling in the number of qubits available on IBM's devices. And if you look at it, then the number of qubits grows exponentially with time. However, due to constraints regarding fidelity, we sort of consider the number of qubits to grow linearly with regard to time. If you look at this progress, then you could go into the conclusion that the field of quantum computing is undergoing rapid development lately. The number of usable qubits is growing linearly in recent years, and the dimensionality of representable Hilbert space follows exponential scale, because each additional qubit sort of adds a new dimension to the Hilbert space, and it doubles the state space. The development trends in quantum computing right now is kind of similar to earlier stages of Moore's law, where the exponential scaling is clearly followed. Now, as of the current stage, we can sort of categorize the development into the concept called noisy intermediate scale quantum error, which represents 10 to around 100 qubits with moderate error rates. So as the quantum computing models are developing this quickly, there arise new security models and implications. For instance, larger device sizes now enable a renewed use for quantum devices, which is to divide the device into multiple spatial segments for simultaneous use by different users. So as of right now, the currently predominant scheme of renting a quantum computer is to rent the device for a full period. This is akin to time sharing of a single CPU core in classical computing. In the near future, as the number of qubits grow, partition-based multi-tenancy or space sharing of quantum computer might become a reality. Now, larger device sizes would bring also complex security implications. For instance, if two users are running their circuits adjacent to each other, and if one of them is malicious, they will be able to extract information from computations on adjacent allocations from another user. Simultaneously, by the same vein, via crosstalk, a malicious user could also influence the computations on their neighbors via crosstalk. The tasks and challenges we're facing are kind of similar to multi-tenancy attacks on FPGAs. And there has already been well-established security work around this topic. So if we want to talk about security measures that counter these effects, I guess one thing that would come to mind of security experts would be qubit space virtualization. This is similar to memory space virtualization. That is, each user could only see the number of qubits and their interconnects as allocated to that user's specific portion. They don't really know where these qubits and interconnects are allocated on which device and on which portion of the device. That sort of brings forth the necessity of fingerprinting as an attack vector. Device fingerprinting would enable multi-tenancy attacks in the form that it enables the attacker to know where exactly their allocation is located and on which specific device. Device fingerprinting would reveal the location of an allocation on hardware, and it virtually allows the attacker to bypass this memory space virtualization technique because there is no physical isolation between qubits given this model. This also enables systematic placement of attack circuits via constraints. So for instance, if the residual space next to some user have some specific topological constraints, then the attacker could shape their circuit and their interconnect use in such a way that this circuit, this attack circuit, will be allocated next to the victim circuit. So knowing the importance of fingerprinting in enabling new attacks on shared quantum computers, we propose a reliable fingerprinting scheme for current NISQ quantum computers. This is based on hardware characterization via ideal tomography technique. And our method is able to perform per device and per locality classification with high accuracy. Per device meaning we're capable of identifying which specific device a circuit is using. And per locality is even more specific. It gives a direct bijection between the physical qubit and the virtualized qubit we're using. Now, this method has been evaluated on state-of-the-art IBM Q hardware, and we will go into this section in more detail. Now, the outline of the talk will be as follows. We've covered the motivation. We will spend a little bit of time talking about the background, followed by threat model methodology and empirical evaluation. Eventually, we will talk a little bit about defense strategies and conclude our talk. So regarding background, for quantum computers, the basic building element is a qubit, and a qubit is sort of akin to a classical bit. A classical bit can take a value of 0 or 1, and qubits can be represented in the 0-1 logical basis as a superposition of these two. And a qubit is an abstraction of a real-world, a physical two-state quantum mechanical system. Now, if you want to define a pure state qubit in the 0-1 computational basis, we can sort of give two basis vectors, which is the 0 ket and the 1 ket. And then we can decompose them by adding alpha and beta to complex factors. And given this normalization constraint, you can sort of go into the conclusion that this qubit state phi can be visualized as a point on the surface of this three-dimensional real unit sphere. And this sphere, this helpful visualization is called block sphere. Now, if we go into a larger scale of a closer granularity, we can talk about an architecture of quantum computers. The basic building blocks now become the qubit registers, which are the registers that hold qubits. Couplings, those are the interconnects between qubits, and those are the enabler of two qubit interactions. And gates, those are similar to classical logic gates. They're operations imposed on one or more qubits. And a native gate set is a set of gates that are physically implemented on hardware. It's sort of similar to, if you look at x86, the machine codes that are understandable by the actual physical hardware. Now, the picture on the right is a coupling map or a topology of IBM Q Lagos, which is a 7-qubit quantum computer. Now, all the couplings here between qubits are bidirectional. If we want to characterize a topology, we described it in graph theoretical terms as a directed graph, where V is just the set of vertices. Right now we have 7, and E is the set of couplings between these vertices. A 2-qubit native gate can be executed on G on this graph if and only if this ordered pair Q1 and Q2 belongs to the edge set or the coupling set. So now that we covered the basics, let's talk about the threat model of our work. We consider two agents in a sort of classical inference and enrollment model. We have an attacker A and a cloud provider P, and all interactions are between these two agents. Now, the cloud provider P manages D devices D1 through D_D with topologies G1 through GD respectively. So A is aware of the list of the devices and their topologies. And this information, we sort of consider that as usually publicized and advertised by the cloud provider. Now, the agent A is able to send allocation requests to P and run circuits on the allocation. These requests come in two types. The first type is full device allocation, where the agent, the attacker A, can tell the cloud backend what device it wants to use, and the cloud backend would allocate the entire device to the attacker if this device is completely free, meaning that this device is not occupied in full or in part. Now, multi-tenancy is another mode where a attacker would ask for a graph constraint, and the cloud provider would provide this an allocation if there is a subgraph among one of those available devices that are currently free. So the special note here is that in the second mode, we don't really know, we as the attacker don't really know where our circuit is actually allocated. What we can see is just a virtualized picture of this G prime graph. So the threat model comes in two stages: enrollment and inference. During the enrollment, the attacker is entitled to type 1 requests, so it can look at each device and draw fingerprints accordingly. However, during the inference stage, the attacker is only allowed to make type 2 requests. So the task, therefore, is for an attacker during stage 2, during the inference stage, to find the exact mapping of an allocation, which is G prime, which is G star, as well as the physical device that that circuit is allocated on, which is denoted by the subscript J. Now, if you look at this model, there is a granularity mismatch where in the enrollment stage, we only collect information on the per device granularity, but we do need to make per locality predictions for arbitrary subgraphs. Our methodology is to create a data structure for the fingerprinting such that if we take a subgraph of the fingerprint that corresponds to a graph, then the fingerprint itself would be a subtree of the larger graph's fingerprint. This model sort of enables us to only look at the full device fingerprint picture for each individual device during the enrollment stage and not care about what specific subgraph we will be dealing with during the inference stage. So then during the tomography, the inference part, once we acquire the information of the subgraph topology G prime, we will make a type 2 request and we will let the provider allocate these specific qubits. And then we run the idle tomography on this virtualized portion of the device and obtains a subgraph fingerprint of G star without actually knowing G star. Now that we know what G prime looks like, we can go back to our enrolled fingerprint and extract each individual embedding's fingerprint that is isomorphic to the G prime graph. In this case, it's just L3, the path graph on 3 vertices, from all the enrollment data we have previously. So for instance, in our 7-qubit device, we can have this as our L3, this as our L3, all the way to the last 3 qubits enumerated. And we feed all the data from these specific local fingerprints into a classifier, and that provides us with a classifier that is tailored specifically to this subgraph architecture. And this is how we're able to extract fingerprints for subgraph topologies and do appropriate classification on them with only knowing full device fingerprints. So the tomography circuits we use follow the standard idle tomography with reference to crosstalk. We have a single qubit actuation on one of the qubits, as well as 2-qubit actuation on a pair of qubits, while putting all the rest of the circuit at idle and measuring the outcome. You can refer to our paper for a more detailed look on our tomography circuits. So we conducted empirical evaluation on 9 IBM Q devices and with the 7 subgraph topologies. The way we chose these 7 subgraphs is that those are the only subgraphs that are smaller than or equal to 5 qubits and that are mappable to at least 2 distinct architectures among these 9 IBM Q quantum devices. So over 12 days, we conducted 9 batches of experiments, and this is the timeline of these experiments. As you see, there is significant delay in some of the batches. This is because there are periods in which the IBM device is reserved for special use or is taken offline for maintenance and recalibration. So if you calculate the actual running time for each full device tomography circuit, the conclusion is it's around 3,000 seconds for 5-qubit devices and around 5,500 seconds for 7-qubit devices. Now, once you look at the collected fingerprint data for each specific topology and calculate the inter and intra separation between groups. For inter separation, we're looking at the separation between 2 distinct embeddings on the same or different batches. And for the intragroup, we're looking at the exact same embedding, the exact same qubit or group of qubits on one device across all 9 batches. So as you see, there is not too much variation in the intergroup. And there is also a small amount of variation in the intergroup. Recall that this axis is in log scale. And these two distributions are very, very clearly separated for every single topology. Now, we take the first 1 to 3 data sets as our training sets and take the rest as prediction. And the result is, as we increase the number of training sets, we observe a higher prediction accuracy for almost all topologies. And overall, as a conclusion, if we only consider batches 0 to 2 and look at the remaining batches as our testing data set, we observe a 99.1% probability of identifying the correct device the circuit is matched on, as well as a 95.3% probability of matching the exact embedding the circuit is run on. Recall that there are dozens of embeddings across the large number of devices we're choosing. So this accuracy is really remarkable. If we only consider batch 0 as the training set and look at how prediction accuracy decays, you could see a moderate decay for most of the topologies over time. However, we should remark that for larger topologies like T5, the prediction accuracy remains high. Now, since we're running out of time, let's very, very briefly discuss the defense strategies. Most of the defense strategies are centered on preventing the execution or obfuscating the execution of idle tomography circuits. We can do a HASP prior to the compiler to detect idle tomography circuits, or we can prevent a metadata or post-level access to the device that would prevent us from acquiring precise timing data that is necessary for high fidelity idle tomography results. We could also impose limit on circuit sizes so that full device tomography circuits are not possible. Another way is to recompile the circuits to insert swap gates in such a way that it does not affect the fidelity of an average computation, but would mess up how the tomography represents the device. And finally, as a note on general optimization, we could use crosstalk mitigation defenses as a way of reliably defending against the idle tomography attacks. However, we should remark that this process, the crosstalk mitigation, is really, really gradual, and it takes a lot of effort into researching more advanced control schemes to make this method an effective defense. Finally, let us conclude our work. The main contributions of this project include developing a data structure and a method for formulating a crosstalk fingerprinting on NISQ quantum computers. And this method is well demonstrated with state-of-the-art devices from IBM. We also proposes and discuss mitigation strategies, and more on this in our paper. All right, thank you so much for coming, and the floor is open to questions.
Okay, perfect. Thank you, Alan, for a great talk. We're a little bit over time, but if are there any questions for Akartishta or Alan, feel free to type them in. I did have sort of question for both speakers. Maybe Akartishta first. I'm sorry if I'm mispronouncing this horribly. How does the method scale to?
Sorry, I was muted. Yeah.
Oh, no worries, no worries. How does your method scale as the circuits become deeper, or as we have instead of 5 or 7, as we have more qubits? Do you have some intuition?
So they can be many more there can be many more future works on this. So it's a very preliminary idea. So you can have future work based on the scalability of the circuits, as you mentioned. You can have work on different types of non-arithmetic circuits, which I'm currently trying to look at. So circuits which have more of the rotation gates or the other type of non-arithmetic gates. and how that will scale on to those kind of circuits. And there your dummy logic will be not restricted to a controlled X gate, but it will be something even more complex, and then you can have a better signature for the circuit itself.
I see. Okay. That's really also interesting.
Oh, I'm
future
sorry,
work.
you're muted. Okay.
Yeah, sorry. Yeah. I was saying that that's also really good, interesting work. And also it's a similar question for Alan about scaling to bigger circuits. Can this method scale, and how could it scale maybe?
Yes. So that is a good question. As we see, there is a sizable scaling from the 5 qubit case to the 7 qubit case. Now, as the number of qubit increases, the method of doing a full device tomography does take longer. However, I'm optimistic about the scaling, as this is more than likely to be a linear scaling. The justification is like this. So currently, for the topologies that are being developed at IBM or Rigetti or other superconducting vendors for that matter, they are using a tileable structure. For instance, IBM has a honeycomb structure where simply by replicating part of the device, you can kind of tile the entire surface. And this is how a scaling is achieved by IBM on the hardware level. So this has a few implications. The first is this tileable way of making bigger quantum computers mean that the average degree of a qubit or a vertex is limited. It is bounded by a constant. So this essentially translates to the number of edges being in scaling with the number of qubits. So that is a O of n scaling, where n is the number of qubits. So for the idle tomography, the data we are using is of the size that is quadratic with regards to the number of qubits. However, as the device size increases, the number of qubits naturally increases, and this means simultaneously we can process a linear scaling amount of data at the same time. So overall, this sort of translates to a linear scaling in the number of qubits for the overall time for a tomography circuit to finish. In my opinion, this is an acceptable scaling because this sort of means there is a sublinear scaling if you divide it by the number of qubits. And this is a natural consequence from the fact that we are able to process more data as the number of qubits increase simultaneously. One way to improve the scaling performance is definitely to sort of take snapshots of part of the circuit at the same time and reassemble the full device picture if possible based on partial data. This could limit the amount of time we need to take for each snapshot.
So I have a question for Alan.
Go ahead.
Yeah, Alan, you were mentioning something about recompiling circuits using swap gates. Is that for meeting the coupling constraints? Can you tell more about that? What were you saying?
Yeah, exactly. So maybe as an example, in the field of quantum machine learning, there is frequent use of a cycle graph structure in optimizing the variational ansatz, for instance. However, in all of the quantum computers we've looked at today, all the 9 devices, all of those graphs are acyclic. So there needs to be a way for the compiler to, to do software optimization tricks by inserting swap gates that relays information from one end of a path to the other end to sort of close a cycle. And in those scenarios, if, let's say, a device actually has a loop, and when the attacker requests for this loop, the provider doesn't necessarily need to allocate that loop to the attacker. Instead, if another portion of the device is free, the provider would be able to allocate that portion and via some software translation tricks. And this would really throw off the attacker because in that case, the attacker would not be able to use topology constraints to narrow down which part of the device they're working with.
Okay, really great discussion. So I don't see any other questions from the audience, and we are a little bit over time. So I think maybe it's a good time to thank all the speakers for coming and giving great talks, and all the attendees for sticking around. So thanks again, Karishta and Alan for the last session. So now I just wanted to again say thanks to everybody. My name is Jakub, and the other co-organizers were Professor Larry Shi and Professor Ruby Lee. So we hope you enjoyed the HASP workshop, and especially also wanted to acknowledge the program committee members again who did great work reviewing all the papers in about a week and a half, and everybody got at least four reviews. So that's really good. So yeah. So anyway, thank you for coming. Thank you for listening. Hope to have your papers in our workshop in 2022, and the papers that were presented today, they'll be published in ACM Digital Library. We're still working on the process, but they should be available soon for everybody. So thank you again, and enjoy the rest of the micro conference. Take care, everybody. Bye bye.